So we start the usual 5-minute slides.
Okay.
Academic 5 minutes. I think we're all here. Yeah, looks very complete. I think we can start. Mark, do your introduction.
This is Patrick.
Thank you, Mark, for the great ever introductions, which I enjoy much. Right, okay. So let's, following the speaker suggestion, make it very informal. So the materials is not going to be light, but that's the way it is. So I cannot. So you see many equations. You should remember that an equation is just a series of words. Okay, that if we should each time express this way, it would just be a nightmare. So it's not something nasty, it's just a way to, to express a lot of things in a very compact way. Okay, so don't hesitate to ask questions. Actually, I will ask questions to you to try to make it as interactive as possible during the lecture. So the plan will be the following. So I will essentially discuss sort of the basics that I will ask. So start with the conservation of energy and the second principle of thermodynamics. Remember very rapidly, because it's not the main issue here, heating, the conservative form of the aerodynamic equations and the shocks. And then I will discuss MHD equations with the, how you get to the ideal MHD, what is behind. We'll do some comment on the Lorentz force. I will then express the conservative form of the MHD equations. I will discuss the important issue regarding the transport of angular momentum, which is something very important in many fields of astrophysics. And we'll discuss a little bit of non-ideal MHD. I don't think I will have time at all to discuss turbulence, so probably if I get to that point, it will already be fantastic. All right. Okay. So let's start with extremely simple stuff. So the internal energy of a perfect gas, which essentially is proportional to temperature. And what is important is that this internal energy is linked to the number of degrees of freedom. Okay, that's something that will be important. So if you take a monoatomic gas, you have 3 degrees of freedom, and each degree of freedoms, when you are at thermodynamic limit, you have an energy which is kT divided by 2 for each degree of freedoms. So this turns into a free half. If you have a diatomic gas, you have 5 degrees of freedoms. So it means, well, because 3 of translation and 2 of rotations, which means that if your molecule can rotate, this element of your fluid can carry more energy than if you are a monoatomic gas. Okay? That's something that will be very important for the problem. All right. And then we have this beautiful, but still a bit mysterious to me, I would say, each time I dig into it. I'm realizing that I never understood it before, and again and again and again, right? So the second principle of thermodynamics, so the internal energy, is linked to the PdV works, so the mechanical work which comes from the pressure, and this a bit mysterious entropy, which as we all know or learn, is a way to measure the level of disorder. But we'll get to that also later on the connection with the fluid equations. Okay, that's just simple definitions. N is the total number of particles, and V the volume of the fluids. Okay, so you can already, using these definitions, replace the volume by the density and obtain this equation, which is just a way to rewrite the equations. Okay. And then you have the continuity equation. I'm not deriving it. I assume you are very familiar with it. There are different ways to write these equations. The most popular one that I should have written here is with the Lagrangian, sorry, the Eulerian derivatives of the density. That's equal to the divergence of the flux. Again, something I will come back to that later. The flux being essentially, in this case, the velocity times the density. But so in the Lagrangian derivative, when you integrated the advection terms, describe this way. And so you can use these expressions to rewrite this one. Okay, so essentially, you use these expressions here, so it's just the energy per particles, and you replace this dn over n squared using these expressions here. And so, written in this form, this is the simple heat equations that you probably saw again several times, which tell you that the variations of heat for a specific piece of fluid is linked again to the PDV work and to again the entropy that we have to account for. Okay? So the heat equations actually is nothing but the second principle of thermodynamics. Okay, that's something that will be very clear when you manipulate these equations. Okay, so the fluid equations and the heat equations, and at the end of the day, the energy equations, are just at the end of the day, the second principle of thermodynamics expressed in a continuous way, in a fluid way. All right. So you will see other forms of these equations. For instance, you can express directly the temperature and rewrite this expression as this. So I will encourage you to dig into those expressions and play around and transform them and go from one form to the other. Okay. So at this stage, the most important message is that the energy equation, actually the heat equation, is directly coming from the second principle of thermodynamics, and it contains, we should not forget about entropy here, which is obviously playing an important role. Okay. We have, of course, possibility to exchange the energies through radiation, and so typically we have to add these net loss functions, which takes into account all the exchange with the environment. So this can be heating if the gas receives photons, or this can be cooling if the gas emits photons. And so what you have to do is actually to go through all the processes that depend of your specific environment. So typically in the ISM, at least in the diffuse ISM, the most important heating would be the photoelectric effect onto the grain, something which had been realized in the 90s. Okay, so not so 30 years ago, but not like 50 years ago. And then, so you have, of course, other sources like cosmic rays a little bit, or X-rays. But in terms of cooling, the most important cooling for high temperature are the Lyman alpha lines. That will work up to maybe a few thousand K. And after that, they were completely unable to cool the gas. And at lower temperature, you have the carbon plus, the oxygen, and a little bit of carbon, and then you enter in the world of molecular. Okay. Again, that's specific to the environment you are investigating, and as we will see, the way the system cool and the ability to actually lose energy has very profound implication on the outcome, on the dynamics of this thing. So understanding how the system is able to lose its energy is something very important. Actually, remember, if you think to dark matter, you know that dark matter dominates in terms of mass the value that matters in the universe by a factor of 6 or something. And but still in the room there is no dark matter, almost. So we are looking very hard for it and we don't find it. Why? Why is there no dark matter in the room?
doesn't interact with photon.
Well, yes, but a little bit more explicitly. I'm just discussing cooling at the moment. Just for you to realize how cooling is important.
Meaning that, so if it doesn't interact with normal matter, it also doesn't have like transition lines to cool itself and can condense down.
Yeah, that's exactly the point. I mean, dark matter essentially is not losing its energy. It has a very hard time to lose its energy, and therefore it gets stuck at very large scales. While we, the baryons, okay, we are very dissipative people, and we can lose our energy, and also we can collapse in ourselves, and become denser and denser, and all this complexity that we are facing now is at the end of the day, it's due to this. Well, not only this skill is particular, but our ability to lose energy in a special way, which is connected to the fact that you have complex structural forms. Right? So you see two different kind of world, just because one is able to lose energy and not the other one. Okay? Right. So cooling time scale, therefore, are very important. So in the context, again, of the diffuse ISM, we distinguish different phases, which I'm sure have been already introduced to you, or they will be in the coming of the week. So the hot phase, so-called hot ionized medium, has a cooling time of very long cooling time of several million of years. The warm neutral medium is about 20 million years, and the cool neutral medium is like less than 10 to about 10 to the 4 years. So it means that the hot ionized medium is almost unable on the time scale, the typical time scale of interest for the ISM, to lose its energy, while the CM, does it extremely rapidly. So you expect this to be more dissipative and to be able to control itself more severely. Okay. So turning now to the conservative form of the equations. So that's the non-conservative form of the equations, except for the continuity that I alluded to at the beginning of the lectures, where you have the Eulerian derivatives and you have the divergence of this flux, which would be something again important in physics. So it's expressed the fact that if you have two pieces of fluids, okay, they can exchange mass through the advections of that mass, but that's it. So if you take a piece of fluid at a specific place, and you bring it at another place through this flux, and that's why mass is conserved. So this is a very convenient way of operating equation. In particular, when you do numerics, it allows you to ensure conservations of mass, momentum, and energy in your code at machine precision level. You can be wrong on the fluxes, but nevertheless, the fact that this is conserved will be correct because the way you have implemented the equation. So the momentum equation is not written in this form yet, and as we discussed already, the energy equation or the heat equation is also not written in conservation form yet. So the goal would be to transform those equations to get these nice properties. And I should add, of course, the viscous tensor here, which describe how energy is dissipated in this mode. Okay, so I'm not going to manipulate the equations here because that's not enough time, and it's not something very convenient to do on a blackboard. But again, that's something I encourage you to do. You have to combine essentially the two equations. For instance, here you can multiply this one by the velocity, and you can add these two equations together. Okay, that brings you to this conservative form of the equation. So in this case, you see you have the Eulerian derivatives and the divergence of a flux. So you recognize a flux similar to this one here. This is the moment that is advected, that is carried out by the flow. Okay, so as you have, say, a stream, the stream carries mass, but it also carries momentum, right? And that's the state which is expressed here. But you also see two other ways to transport momentum. One way is through the pressure. So it means you don't have necessarily to transport mass to also transport momentum. You know, if you just push gas, you will transfer some momentum, and that's one way to do it. And there is another one, which is the viscosity, which also lets you to do so. If you have two streams of gas like this, just by viscosity, the one that is not moving initially is going to be put in motions, you know, by the transfer of the momentum from one to another through viscosity. All right, and you can do the same with the energy equations. So the difference, the heat equations, is then transformed into the conservation energy equations. So you have again to combine those three equations. So you will multiply, for instance, these equations here by v squared plus the internal energy. This one you multiply by the velocity, and you sum all of that together, and you can then, you know, put all those terms. So again, you see this Eulerian quantity, the total internal energy, kinetic, and internal energy of the fluid, the flux. So again, advections, pressure, an internal energy flux, and a flux carried by the viscosity. And you see some remaining terms. So one is again this entropy that comes, if you remember, from the second principle of thermodynamics, so you can track it down. Okay? So it's there in the final conservation energy equations. And the terms that you cannot put as divergence, which come from the viscosity, and which express the fact that you have energy dissipation, so the flow is irreversible. So you convert energy into heat, essentially. And at the end of the day, you would like these equations to be zero, because you say, okay, I believe in energy conservations, so I want this to be zero. So this automatically leads you to equating your entropy with the dissipation of the flow. Yes?
Can you not have time changing viscosity for your gas or medium?
Yes, you can probably have it depends on the nature of your flow. I mean, then it probably has to be done through some interaction, or you may have some temperature dependence on the viscosity. So, yeah, in principle, you could have that. Yeah. And so the important point here is that you now have an expression for the entropy if you want these equations to be zero. And so you can come back then to the energy, the heat equations initially, and replace the entropy that we had by the dissipation of the fluid. So now you can interpret the viscosity as, in this case, the entropy as in this case being due to the dissipation of the fluid through the viscosity. So the entropy is linked directly to the irreversibility of the flow that manifests itself through the viscous dissipation. In other equations, or for instance, in the non-ideal energy equations, we will have different forms for these terms, which may be, for instance, linked to lambda diffusions and to all other types of dissipation. Each time you have an irreversible processes, okay, it will have the signature there. So it will create okay. So shocks. So now we have the the conservative form of the equations. So the important message, or one important message of this equation, is described here. You have a flux coming here, okay, and you have a flux coming out. Okay. So if your equations is written this way, so a quantity which is the time derivative of this quantity and the divergence of the flux, okay, you can transform this equation, and you can relate the variation of the quantity inside the volume of control, these things, to the incoming flux. So this and that. And so if you consider a very, very tiny volume here, so if this thickness here goes to 0, okay, then these terms here will go to 0 because the length shrinks, but the surface can be maintained big, and so at the end of the day, only the flux term will survive, meaning that you will have the equality between these two flux. Okay, so the message, the important and interesting message of the equations written in their conservative form is that the flux, what goes inside the divergence, they must be continuous in any point. The quantity themselves, maybe not, as we see, but the flux have to be continuous. Okay, so this means just taking out the flux that we saw at the previous view graph, that those quantities, they must be continuous. So in that case, 1 and 2 refer to this sort of side 1 and 2, and separated by an interface. So of course, those are very important constraints, and it turns out that you can express, using those jump relations, you can express the ratio between quantity 1 and quantity 2 as a function of, usually we use the Mach number because it's, we believe, the most relevant parameter. It could be something else. So the Mach number is the ratio of the incoming velocity divided by the sound speed. Okay. So we use the Mach number as a way to describe these situations. And so you can express, for instance, the ratio of the density at side 2 divided by density at side 1. So how density will jump through this interface. And so you express this as a function of the Mach number. You can also immediately, with the continuity equations, see that the ratio of ρ2 and ρ1 has to be equal to the ratio of v1 or v2. The perpendicular sign here means that we consider only velocity perpendicular to the face. So that's it, that's linked to the Mach number. We can now look at some special cases, but before that, I would like to ask you, I started the lecture by discussing the number of degrees of freedom. So the monatomic gas has 3 degrees of freedom, and the diatomic gas has 5 degrees of freedom. So do you think that the shock for the same Mach number, you think that what would be what compressions will be more important? Is it for a diatomic shock or for a monoatomic shock? For the same Mach number? What do you think is going to get more compression? the density enhancement. Just for intuitions. So what's happened in the shock? Can someone describe? So those are equations. As I said, you have words behind, but it's of course important for each equations to have physical intuitions behind, and that's what we give you or guide you through the manipulations of those equations. So, what can someone describe with his or her words what's happened through a shock?
Yeah, you compress the gas
Yes.
and you heat up the gas, you give energy to the
Okay.
agent.
Yes. So, which means exactly that you convert kinetic energy, okay, into heat energy. All right. Okay. So based on that, or maybe some of you know the answer already. Do you expect the monoatomic gas to lead to a stronger compression,
Yes.
or the diatomic gas? Which one?
Naively, the monatomic gas.
So okay? Other opinion?
The atomic has more degrees of freedom, so there's more places to
So the monoatomic, so the diatomic has more degree of freedom, which means that each free element is able to carry more thermal energy. Okay, so it means that as you convert the kinetic energy into thermal energy, okay, the final temperature is going to be lower for the diatomic gas because you need more kinetic, thermal energy per fluid element. And so when you look at this compression factor, ρ2 over ρ1, a monatomic gas has gamma equal 5/3. So if you just look at the limit of infinite Mach number to make it a bit simpler, you can just replace, and you will see that the compression factor, the maximum compression factor you can have for the monoatomic gas is actually 4. Okay? For a diatomic gas, it's 7/5, so the gamma is 7/5, and we find that it's equal to 6. So the compression is actually larger for diatomic gas than for monoatomic gas. And the reason is that the shock is many things, but amongst them is the conversion of kinetic energy into thermal energy. Okay, and then you are spreading this energy over all your fluid elements, but because the diatomic gas has more internal degree of freedom, the temperature that will result of this exchange is weaker because you need more thermal energy to bring it at a higher temperature. Okay? And in the limit where you have an infinite degree of freedom, which sounds a bit crazy, but it's not that crazy for a reason I will tell you in a minute. So in this case, it is equal, formally equal to gamma equal 1. And in this case, you can see that the compression you can obtain in a shock is actually very large. I mean, it's proportional to the square of the Mach number. Meaning that if you get a very, very strong shock, you can compress infinitely, or proportionally to the square of your Mach number, your medium. So it's a very violent response of the flow, which is different from what you get in a finite degree of freedom shock. So the reason why this case is not fully academic is because of the cooling that we discussed just before. It turns out that if your cooling processes are efficient enough to radiate away energy in a relatively short amount of time, so that's typically the case for the cold gas, so that's why I was discussing the short time scale for the CNN, but you will find a similar short time scale for the molecular gas, for instance. So in a very short time scale, meaning a very short length scale as well, the energy is going to cool, is going to be, sorry, the gas is going to cool, the energy is going to be radiated away, and you quickly come back in many situations to something which has more or less the same temperature that you had before the shock. So maybe I can draw something because I don't have view. Okay, so if you try, hope you see it. Okay, so if you have, say, space and say the velocity like this, so you have a supersonic velocity, the shock, okay, and then a subsonic velocity. If you now represent the temperature, okay, so your temperature may be, say, constant before the shock, and then at the shock, energy is conserved on a very short wavelength, also a very short scale, and then after that you get a fast cooling, like this, and after the shock, you more or less recover the temperature you had before. Of course, it depends on the cooling machinery that is behind, so this is not a theorem, but in many cases it will be the case. And so in this case, if you apply the Rankine-Hugoniot between these two points, then you will virtually be in the situation of gamma equal to 1. Okay? And so in this case, you can get a shock with a very strong density enhancement proportional to the square of the Mach number. Okay? So in the context of this school and for the star formation in general, of course that's something very important because the whole story of forming structure in the universe is how you crank up the density essentially. Okay? And of course gravity is, I would say, is paid for that. But sometimes, and very often actually, gravity needs some helps to do the job, and that's one way to do it, to start the process. Okay, okay, so now implicitly here and also there, I've been assuming that the shock was between supersonic flow, which becomes subsonic. So it's sort of split, a supersonic medium and a subsonic medium. But as you see, at the end of the day, I decided to write ρ2 over ρ1, but I could have done the reverse. I could change 2 in 1 and 1 in 2, in which case I may have decided that I may have turned my arrows to the other side and go from a subsonic to a supersonic. That sounds correct. So why? I mean, you see my point is that the equations, the other equations, they are. I mean, I can change the time sign without any problem. So I can decide to go from 1 or 2 and 2 to 1, the same thing. But this doesn't sound right. Why?
Entropy.
Yes, that's because of entropy, so that's why you should never remember this, okay? You should never remember that, okay? That anything you do, at the end of the day, goes back to the second principle of thermodynamics. So, and of course, even if you don't remember, you have to teach your code, because your code may not be aware of that. And code are very good at not, knowing the basics, the basic physical processes, and so this has been a problem for a while. That some code that were actually not respecting essentially the second law of thermodynamics, and you have what is called rarefaction shocks. So the shock that I just described, where you actually jump from subsonic medium into a supersonic medium. So these violate entropy, and so you must write codes which, by definitions, will respect will respect entropy growth to scratch. Okay? So the modern code usually they do it, but you still have to worry about that. Okay. Right.
Sorry, so what happens when there is dissociation? So that would be like changing gamma from one side to the other. So how is that treated? When there is dissociation of same molecules in the shock,
Yeah.
so how is that treated?
Well, then you have to have ionization equations in this case. So to add this in your equations, and I mean they are
It's not
dissociative shocks.
formulated in
Sorry.
terms of- It's not formulated then in terms of gamma? Because
I think it depends. Yeah. I think you have to. In some cases, you can probably. But it depends how dissociative is your shock, and it depends also what physics exactly you want to describe. It's a bit like the cooling in a sense. Because in many codes, for instance, the cooling length is not solved. Okay, so in this case, you are not seeing the density jump, sorry, the temperature jump, because you have just one cell is shorter than the cooling length. So you have similar issues with the ionization. Okay, if you really want to describe the ionization in detail, if this is your interest, then you probably solve directly the field equation, and then you will describe you will produce situations where you will be out of equilibrium for the ionization, okay? And then you will have a sort of the equivalent of the cooling length, which would be a sort of ionization length, or whatever you want to call it. So it may depend of your resolutions. So I don't think I can give a very general statement. It depends of your interest and the problem. All right. So I'm turning now to the Maxwell equation that I'm sure you know very well. So the Lorentz force is given by these expressions. And you have here to make an important distinction between the lab frame, where you have this velocity, and the fluid frame, where, by definition, there is no velocity because the fluid is at rest. So if you believe that the force is Galilean invariant, then you must have an equality to satisfy this relation. So the electric field must not be the same in the fluid frame and in the lab frame, but the magnetic field, on the contrary, has to be the same because of the velocity here. Okay, so it means that if you assume that your fluid is a perfect conductor, which is a very simplifying, very easy assumption, then the electric field in the rest frame has to be 0, and so you get an expression, you get that the electric field has to be minus V times V. Okay? So that's very convenient because it allows you to, for instance, close these equations. And now you know the electric field, so you have an equation for the evolution of the magnetic field. Okay? So that is really what is behind here when you see the what is called the Faraday equation, this one, which is used in many ideal imagery codes. You have to remember that the assumptions which is behind, the important assumption which is behind, is this one, that the electric field is assumed to be zero in the rest frame of the fluid, which is a very strong assumption. Okay, so these equations can be recasted in this way. So you can split this operator to have an advection, a divergent part, and you see I just wrote here the continuity equation in a similar way. So the advection term is present, and the divergent terms, which express the conservation of mass in this case, is also there. So those two terms, they are not new, they are also present in the continuity equation. But there is a new term, which is not present here. It's B, okay, B times grad V. So B times grad V. So it's associated to the very nature of the magnetic field, which is an array and not which is a vector or not a scalar. Okay, so it means that if you write it explicitly, the different components of the magnetic field, they are coupled to each other through this term and only through this one. Of course, they have to satisfy dV equals 0, but essentially, if you have, say, a By in the problem, okay, and just put a random velocity field, you immediately generate a Bx and a Bz component because of this guy here. So to get another maybe more visual way, okay, if this is your field lines, and if my hands describe motions, you know, as I move, I create a new component of the magnetic field. Okay, so that's a new way, a vectorial way to create a field, and it's very important for our universe. Do you know what these terms at the end of the day is responsible for? I'm sure you know the answer. Dynamo. Okay, so the reason why we have magnetic field in the universe is largely because of this guy. Because, as I said, it can create from one component of the magnetic field, it can create another component of the magnetic field. So if you have like Bx generating By and By generating Bx, okay, you can get an exponential amplification. And that's time. So that's a way, again, to convert kinetic energy into magnetic energy. Okay. So an important properties of the magnetic field that I'm sure you are aware of is the conservation of the magnetic flux. So the magnetic flux is expressed, so the integral of the magnetic field over a surface, and you can demonstrate that the magnetic flux is a conserved quantity in ideal MHD. Okay? So this is known as magnetic field being frozen into the fluid, and there is sometimes confusion that magnetic field being frozen should imply that you have a correlation between density and magnetic field. This is not the case. And you can have complete decorrelation between the field, magnetic field and the density. It depends on the type of waves you have. If you have something that I will not have the time to discuss, like fast waves, meaning that the velocity of the waves is typically the sum of the sun speed and the atom speed, and then you get a correlation. But there are other waves, like the slow wave, where you get an anti-correlation. Okay? So at the end of the day, they are not correlated. Okay? Right. Just some comment on the Lorentz force. Maybe I think I should hurry up a bit. So maybe I will be fast. Okay. So if the motions are slow with respect to the sun speed, sorry, the speed of light, so you can neglect the displacement current in the Maxwell equation, and then you have a direct relation between the curl of B and the curl of G. And so the Lorentz force, which is G times B, can be written this way. And then you can split it into the magnetic pressure and the magnetic tension. So the magnetic pressure is what you get when you have like packed field lines which are close to each other. It tends to, exert a pressure. They want to get away from each other. And the magnetic tension is when you try to bend the field lines like this. I'm not going to break these things, but you see, if you try to bend the field lines, it tends to come back straight, and that's the tension. And that's this times here is also very important. It will be in particular responsible for the transfer of angular momentum. Okay? The reason why magnetic field is so different from magnetized flow is so different from an hydrodynamical flow is because of that guy here, which introduced a completely different behavior. At the beginning of the lecture, at some stage, I was commenting on the transport of momentum through viscosity. If you have two flows like that, they exchange some momentum because of this viscosity. But you see, in most cases, it remains weak because the viscosity, in most, or in many fluids at least, and particularly in astrophysics, they are not very viscous, and so it's a very weak contribution. But if you have a magnetic field threading the two the fluids again, you immediately see, for the very same reason that you generate a new component. If I try to do that, it's not possible because they are linked to each other, and so you have to fight against the field lines because of the magnetic tension. So it means you introduce like a strong memory into the flow. Okay, you cannot just, if you do this in hydro, okay, so you don't forget the signal. In MHD, you remember, because you have created a new component. All right. So you can, so that's the MHD equations with the force, the Lorentz force, and the induction equations. You can, I will be quick, sorry. You can also obtain a conservative form, which are written there. So you can write the momentum as this Eulerian derivatives plus the divergence of this operator. And you see now the magnetic field, it can be seen as a way to transport momentum, as a flux of momentum, of linear momentum. If I have time, I will discuss in a sec angular momentum. At this stage, it's still linear momentum. Okay? So that's because of the pressure and the tension. And you also have a contribution in the energy equation, which has to do, at the end of the day, to the Poynting flux that you probably saw in electrodynamics. Okay, a little bit of MHD shocks. So, as we wrote the continuity of the flux in hydro, we can do the same in MHD. So that's again the MHD equation in the conservative forms, and that's the jump relation. So expressing essentially the continuity of all the fluxes at any interface. So this one is unchanged, but all the others are changed. And in particular, there is an important difference, is that now you have to worry about the transverse component. So you have a shock like this, okay? My hand is a shock, the velocity is like that. In the hydro case, we worried only on the perpendicular component. But it's not possible for the MHD case, because now I have this coupling between the various components of the flow through precisely the magnetic tension. Okay, so the magnetic tension, for instance, is there, B perpendicular and B parallel. And this makes that you have the flux, this guy is the flux of transverse momentum that was there in hydro, but which is not relevant because the parallel velocity to the shock is conserved, strictly speaking, in hydrodynamics. It's not the case anymore in MHD because of the magnetic tension. Okay? So, generally speaking, MHD shocks are orders of magnitudes more difficult than hydro shocks. There are still a bit of research going on onto the MHD shock, so it's not a fully resolved problem. I'm just picking one specific example, which I think is very fundamental and illustrative. You can actually have something like a shock with without a discontinuity in the perpendicular velocity, which sounds a bit strange because usually a shock sounds like, okay, I jump from supersonic to subsonic. Okay, so I change this perpendicular velocity. Actually, in the MHD, there is waves discontinuity, which is called the transverse rotational discontinuity, which entail no variation of the perpendicular velocity and no variation of the density. Okay, so these two fields will be constant, but you have a discontinuity of the parallel velocity and of the parallel magnetic field. Okay, so at the end, when you combine things, you find that this is actually an Alven waves, like a discontinuous Alven wave. So, like a nonlinear Alven wave where you jump from one transverse state to another one. Okay, so that's called the rotational discontinuity, and that's a new beast which again does not exist in the old American context, which is specific to MHD and which is come again to, or which is bounds back to the existence of the magnetic tension. Okay? Right. So I would like to finish with the transport of local momentum, which is again something that is very important. So I start from the hydrodynamical equations, so the one that we saw already, but this time I use the cylindrical coordinates because this is what is needed to discuss the momentum, and I'm writing only the azimuthal component, so what is usually designed as rotation. Okay, so V phi is the rotation of the fluid. Okay, so that's the way it writes in those coordinates. So it's essentially the same, except that you have these curvature terms, which comes from the particular choice of coordinates. Okay, so we can, as for the conservation form of the equation before, we can actually transform these equations, combining it with the continuity equation, okay? And we express it with, again, Lagrangian derivatives and a flux. And you see this concept quantity now is density times the velocity, the azimuthal velocity, so the rotation, and the, should not forget, and r, the distance. So this is a momentum, okay? Rho v phi times r being the level arm, this is the usual momentum, okay? So you get that in some circumstances in a system, okay, the momentum can be conserved. And then you have a flux, which at this stage is essentially or exclusively carried by the velocity, so it's a transport flux of momentum. The pressure is also there, but as you see, it's oriented toward the azimuthal directions, so it does not transport any momentum. Okay, it just stayed in the system. Okay. If you now include the magnetic field in this equation, okay, you can follow the same transformation, and you can again write the Lorentz force. You have to use dV equals 0, and you will see in these equations this term appearing, which is V phi times B, V phi times B. Okay. So in particular, along the radial directions, you will have B phi times BR, and along the z-axis, you will have a B phi times BZ. So those two terms, they correspond to what we call the magnetic braking. That's a flux of angular momentum that can be exchanged, usually carried away from your system through the magnetic field. And again, this is linked to the magnetic tension. So to get a physical picture, I like to have in mind this unusual setup, but you can construct it very easily. Okay, if you take just plates, okay, and you connect it by a series of of string. If you move the plate that is say on the bottom, okay, you will create a tension, and the plate which is on top is going to be put in rotation as well. This is magnetic braking. Okay? Exchange of angular momentum through the tension of the field lines. And of course, it's a very powerful way to exchange magnetic braking in an astrophysical system. This is true, as will be discussed later, for protoplanetary disk or any kind of disk. It's also the case for stars. Through wind, for instance, at the start limit, you can transfer angular momentum through from the star to the wind and carry it away. Okay. All right. You can have similar things with gravity. Okay. So again, you come back to these equations. So the momentum equation written in cylindrical coordinates. So you have to worry about gravity. And the trick here is to use the Poisson equation. So Poisson equations, written again in cylindrical coordinates. It sounds at the very first sight to be very complicated because you replace this simple density by this ugliness. Okay? But it turns out it provides some simplifications, because when you combine this with G phi, you can actually transform your equation in this way, okay? And rewrite your final momentum equation. So that's the momentum equation we have been manipulating already. You have the advection of the momentum, you have the magnetic braking, and then new guy here, which is the gravity. So gravity, it can be seen as something which has a pressure, but a negative pressure. Okay. So you see the sign has changed between the magnetic pressure and the standard pressure and gravity. Gravity is attractive. but there is also a sort of gravitational tension, which, as you see, is surprisingly similar to the magnetic tension. It's actually almost the same. You have to change the sign, but apart from the sign, that's exactly the same. It's surprising. You have to work a little bit, but it's very, very nice to see. So, at first sight, you may say, oh, but well, then gravity and magnetic field, they run the same way, so they should be the same. Well, no, there is a fundamental difference. There is a fundamental difference, which is the source equation, because the source equation of gravity is the Poisson equation, so it's linked to the density, while the source equations of the magnetic field is the Faraday equation. And in particular, if your density field is axisymmetric, so will be the gravitational field. So if, for instance, the disk or the star is fully axisymmetric, then there is no g phi. And so there is no gravitational transport of angular momentum. But this is not true for magnetic field. You can still have a toroidal field even if you are purely axisymmetric. That's because the force of the field are not the same. Okay, so that's a very, very fundamental difference again. Apart from that, gravity is a very powerful way to transport angular momentum because of this expression. And but for that, you need typically to have something like a spiral weight, some source of non-axis symmetry. Okay? And that's something we also see. I'm running late, so I don't know whether I should go for non-linear MHD.
I think in the interest of giving Amy her hour, we should probably break here.
I'm okay with non-ideal MHC, Patrick.
Okay.
Okay.
It's okay with me. But
So,
thank you.
okay, so I try to make it short then. Okay. So as I discussed before, the ideal MHD comes from very simple minded assumptions, which is that the fluid, your fluid, should be a perfect conductor. So if you remember, this means that the electric field in the frame of your fluid is zero. So physically, it means that the electrons are rearranging themselves, to cancel out any electric field, which is more or less what you have in a metal. But of course, this is a very strong assumption, and it's not going to be true in general. So, to deal with it correctly, you have to do some efforts. You have to first deal with the problem in all complexity. At the end of the day, that's what you have to do for MHD. So you have the equation for neutral. They will feel the ions and the electrons friction, but no magnetic field because they are not charged. Then you have the equation for the ions. So they have a Lorentz force and the frictions between the ions and the neutral, and the same with the electron. Okay. And it turns out that in many places in the ISM, particularly the cold ISM and particularly the star-forming ISM, the ionization is actually very low. Very, very low. I mean, in the cold gas, it's 10 to the minus 4. In the dense gas, like molecular clouds, it can be 10 to the minus 7. In the very, very dense gas, it can be 10 to the minus 10. So 10 to the minus 10 for me is crazy. Huh? If you think in terms of number of humans on Earth, it's like there would be one human carrying out the magnetic field for all humanity. It's still a field. So this is crazy, but okay, way to work sometimes. Okay, so in any case, because of this low ionization, you can neglect the inertia. So that simplifies the problem. Then you have, at the end of the day, it's you make the approximations that the ions are at mechanical equilibrium. So the friction between the neutral and the ions has to be equal to the Lorentz force, and same for the electron. Okay. So then you You can combine this, also taking into account electroneutrality. So you can add this equation, and you can relate the Lorentz force with the friction of the ions and the neutral. So you can then plug this back here, and with these approximations, thanks to this relation, it's like if your neutral would be feeling the Lorentz force through the interaction with the electrons and the ions. Okay, so that's why we often forget that the neutral don't feel the Lorentz force, and we all bravely write, the Lorentz force in the neutral equations. It's because of this result, and this is justified only if the inertia of the ions and electrons can be ignored. All right. So now we have to worry about those expressions of those frictions. So you have coefficients in front of them, and this comes from macrophysics calculation that I will not discuss today. There are papers where these things have been calculated. So it boils back again to the macrophysics. So it's a bit like my comment about the cooling. The cooling is very much related to the detail of the macrophysics, and it has huge consequences on the microscopic organization of the universe. The same is true through the coupling here, which at the end of the day will have consequences of how the angular momentum is transported. All right, so you can produce, what is missing now is an equation to describe how the magnetic field evolve, and that's called a generalized Ohm's law. So the small trick is just to do that actually, because if you assume that the ions are well coupled to the magnetic field, that will be the relevant velocity which appears in the Faraday equations, but you want to express, you want to, in a sense, ignore the presence of the ions as much as possible. So you would like to have essentially an equation that entails the velocity of the neutral, and so you write this as a difference, Vi minus C, okay? And so you combine, taking again the equations, this one here, okay? You combine these equations where you have the velocity of the ions which appears, and you essentially replace each time you see a dy by this expression. I'm going a bit rapidly and just giving you a flavor. And at the end, you can express the electric field as the same term than what you would get in ideal MHD, which comes from the perfect conductor assumption, plus some correction. So you have an ohmic correction here, which comes from the friction between the ions and the neutron, sorry, the electrons and the neutron. You have the ambipolar diffusions, which describe the way that, how the neutral decoupled from the magnetic field. And you have the Hall effect, which describe how the ions decoupled from the magnetic field. So each terms, carries its own piece of physics, and depending on the conditions in the ISM, it can be dominated by one term on another. So typically, in the more diffuse ISM, diffuse in my mind is less than 10 to the 7, 10 to the 8. So my definition of diffuse can be different from yours, but typically most of the times we are dominated by the ambipolar diffusions. But when we get to denser material, the Hall effect and the very high density, typically when you enter the first Larsen core that we will discuss this afternoon, you get a very strong ohmic resistivity, and you almost get decoupled between. You get almost complete decoupling between the gas bands and the magnetic field. So all these terms have to be accounted for. Right, and so at the end you get this equation. So you have corrections from the ideal OHD, and the strength of these corrections again depends on the medium. So you have to calculate, in the worst case, calculating those contributions can be difficult, particularly when you have dust in the problem. The dust, they will carry charge themselves, so this will be another layer of complexity. The grain, they can coagulate, it can exchange charge and so on, so it becomes something very nasty and very complex. Just to give an example of some resistivity which have been calculated. So this is the magnetic diffusivity, this is the density, so that's 10 to the 4, so dense core conditions, that to 10 to the 12. You see the Umpar diffusions, which is dominating, the Hall effect, and the ohmic one, and the difference between these curves, it depends on the detail of the dense grain assumption. So it's a complicated business. Okay. So I think I will stop there, and thank you for your attention.
We will forego questions in the interest of time.
Oops.
Pass to Amy. And while she's setting up, I will note there's still a few chocolates left. I'm being a little more parsimonious with them than yesterday because we're running low, but they're still available.
Please don't worry. So I have to apologize to you guys. I slightly miscalculated this morning and I'm a little bit under caffeinated. But I'm gonna try to keep a good pace so that we have a good coffee break and a nice conversation then. So the title of the talk is Observations of Protoclusters in H2 Regions. I think it's gonna mainly be about protoclusters. We haven't covered that too much yet. So, start with the question, what's a protocluster? Well, I don't know, when I was in grad school, like I said yesterday, I would often Google things. There's many, many terms. We're like overloaded with jargon. So we're like, oh, this person's talking about protoclusters. What's a protocluster? Everything I found the other day was about these high redshift things. It's not what we're talking about, okay? Obviously, they were defined yesterday, but for the purposes of this talk, we want to talk about things like Orion, perhaps, and in the Milky Way that are gas dominated. They haven't yet transferred all of their mass to the stellar component, or any way or destroyed it or gotten rid of it. And that's sort of a basic working definition. Some people gripe about the use of protoclusters, don't like it, blah, 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 but anyway, it's a working definition for the time being. So later on in this, meeting school, we're gonna have more and more discussion about extragalactic, right? So we can ask ourselves, what is known about star formation, protocluster formation, or cluster formation today, right? What comes to mind from that point of view? And I think this is probably the first answer. Kennicott-Schmidt relation, I'm guessing we're gonna see a lot of this type of plot. Where we relate the gas column, where the stars are forming, to some estimate of the star formation rate. Maybe this comes to mind, this train wreck of colliding gas and dust, triggering many star-forming regions on large scales, right? Or maybe this thing comes to mind, fireworks galaxy, where we've observed order 8 or so, directly observed 8 or so supernova. But these measures and prescriptions of star formation are tracing these high mass stars, which have really short, they seem long, long lifetimes, right? Sorry, I'm scrambling my words, undercaffeinated. They seem like they have short lifetimes compared to the overall timescales that we're dealing with in the universe, but actually, they have timescales of formation that are much, much longer than the timescales that we talked about yesterday. So it's like looking at star formation once stars have already started to die, right? Once they're exploding in supernova. So to get at this concept of protoclusters, formation of star clusters, we want to use some of these laboratories we have that are more nearby where we can detect star formation on the timescales where the stars are actually forming, right? And we might even go into the core phase. Not all cores are forming stars, but anyway, it's where stars are thought to start to get at these processes. So, also, I think another very relevant point is that these are actually the energy injection scales for processes like feedback. These small scales where some of these massive stars are actually forming, right? And so we want to use all of from the observational point of view, the machines that we've had in the past, the machines of today, and the machines that are, coming into their own today, or in the near future, to get at this problem, right? So we want to analyze physical systems where we can actually observe this process as it develops at the resolution of the energy injection scales. Does this make sense, guys? So we see these external galaxies, which are, this beautiful data, like this pause example of the whirlpool. And we're going to zoom in hopefully to these Milky Way, hopefully these are analogs in these disk systems to try to get at these types of problems. Now, if we try to do this in our solar neighborhood, in our immediate neighborhood, we can't really get at this problem because we only have one sort of GMC, let's say, getting at the mass scales that we're interested in that we can detect in the extragalactic systems, right? We're not talking about these fluffy torus things, right? Talking about something that even though we think this thing will form a cluster that'll disperse, it's not a globular cluster or something like that, but anyway, it's getting to be in a more relevant mass regime. And then we're also going to look at some more distant but still Milky Way protoclusters from the ALMA IMF survey. And so the idea here is that these systems provide this key link so that we can jump from our galaxy to, spiral galaxy analogs and so on, where we just cannot, in the foreseeable future, obtain the same level of detail and resolution. So one question that I think you're going to address later is the efficiency. I don't have an answer, but a common answer is, quote, the magic of feedback, right? But there's a lot of questions about how this process operates. I'm not going to address any of that theory, but anyway, we have to, on some level, deal with it because we have to destroy a bunch of molecular cloud mass or consume it. Anyway, we've got to do something with it. And so this is a little bit analogous to the sort of cartoon that Nadia showed us yesterday, where you have gas-dominated phase, this intermediate sort of star-forming phase, and then the naked clusters, right? And she's trying to relate these time scales. So we have these different processes that we need to be working on. And if we kind of pick on people in the field, in these different fields a little bit, what we have is a big disconnect, at least in my opinion. And we would like to, in the future, integrate these disconnected fields. These people, and this is a quote from people working on sort of, quote, galaxy scale emergence of clouds. They start working on it, and then they get nervous about star formation. They're like, no, I'm not even working on star formation, right? And then you have people like me right? Where I'm like, I don't know anything about the other two, I don't wanna talk about feedback, I don't wanna talk about these other processes. And then you have the people that are trying to address the feedback processes and sort of how we get rid of all this molecular cloud mass that seem to kind of ignore the rest of us. And so we want to build these connections so that we can build this coherent evolutionary picture from, you know, the beginning to the end, where the end is a star cluster with no mass, no gas mass left, right? So that's sort of the basic idea. Can we really even separate these stages? You know, there's a lot of questions here. I don't have a lot of answers, but anyway, that's sort of the notions that we're dealing with. And so, trying to keep this a little bit narrow, you know, I said I'm gonna talk about Orion, I'm gonna talk about LMIMF. So keep it simple. You know, what has Orion ever done for us? You know, to quote Monty Python, or to paraphrase them, you know, it's nearby, it's bright, it's observable from both hemispheres. It's a literal shitload of data there. So it's a good test bed for ideas, right? And it's nearby, so high resolution. It's a GMC. Why do we care about the 10 to the 5 M-sun scale? Do you guys remember from yesterday? I'm like, I forget everything post-pandemic, so.
It's the bone mass of GMC.
Hopefully it's a representative laboratory. I mean, every cloud, if you look at enough detail, is a weirdo, right? But, good catch. Looking in enough detail, every cloud's a weirdo. But hopefully this has some measure of, you know, being representative, or at least we can argue that. So that's good. It's also an H2 region, and it has this protocluster in the north, and this integral shaped filament, this little noodle thing that's curvy. So it's also full of these filaments that Johnny was talking about. So it's following conventional wisdom well enough. And one of the things that we did is we took this Herschel column density map, which I didn't discuss too much yesterday because Mark outlined more or less how these maps are generated. But think of this as a mass map. We draw a ridge line, which is similar to these little lines that Jonathan showed. In this case, our ridge line is even more simple. There's no fancy algorithm. We just follow the maximum of the mass or column density through the map, record it, straighten out the filament to make it simple, and get an average line mass as a function of, let's say, impact parameter from that ridge line, so projected radius. And this is what we get. We get this power law. And so this thing, I mean, here's the expression. I mean, R is really, projected radius, so keep that in mind. But anyway, what was the number that Jonathan said yesterday for the sort of so-called stable filaments, the limit? It was like 16 M-sun per parsec, 16.2, 16.6, something like that, right? So this thing's a monster compared to that estimate. And even if you say, okay, but maybe that was at 0.1 parsecs and not at 1 parsec, at 0.1 it's still at 160 something M-sun per parsec, so at least a factor of 10 above that. So what's going on with this thing? That's one question. Another question is how are we in the field plotting a single value for the mass per unit length of filaments when we actually know we have this density distribution, right? So one thing I didn't mention is people don't normally plot things like this, but anyway, this is cumulative. So that's why it's growing as we go out. But anyway, we have a continuous distribution, so we can't really, if you truncate this at 0.1 or 1, you're still going to be missing mass. So we have to be, I think, careful about how we think about these filaments. But anyway, we're already thinking about filaments, so we're injecting this notion of a cylinder, right? So you can decompose this with a 3D model into a 3D density field or a gravitational potential, and you can play these different games. I'm not going to get into that too much here. Stay close to the observation so we can ask where are the protostars and where are the quote, still super young, but more evolved class 2 disks, so stars with disks. I see stars there, but they're really stars with disks. Okay, so keep that in mind. Timescales from yesterday, we recall order 2 million years for these guys, 500,000 years for these. So if we focus on the northern filament up there, I like the stick. So the integral shaped filament, this curvy thing, you know, all the protostars that we can find are like beads on a string. They're just glued down to the ridgeline, right? And except for like, maybe there's like one exception or whatever. But anyway, they're at the bottom of the gravitational potential well of the cloud, so they're kinematically cold, and they're stuck there. And then a little while later, we look at these disk stars, and they're spread out, right? So how did they get there on these short timescales? That's one question. And this sort of concentration of points here is the center of the Orion Nebula cluster on 42. So we want to think about how this situation has come about. We can analyze the integral shaped filament with its little ridge line and its little hiccup here in a little more detail. And we can also compare that to the mass distribution of the stars themselves to try to get at gravity of both systems, right? So for that, like I said, we need this model because we have everything projected on the plane of the sky. So for the stars, we want to say, okay, you know, first order sphere, and we only have 2 geometries really that we use, right? Cylinders and spheres. So that's what we're going to use here. And we recall, you know, we have this pictorial representation of this cylinder, but anyway, it's this, you know, it's varying with radius, right? Where the density is decreasing as you go out, and it's centrally concentrated. And this would be the gas component, and this would be the star component. So we can play some games, play around with you know, density, assuming these models, which are probably wrong, like I said yesterday, but they're working, you know, tools. You can plot the densities and the gravitational field of these things. And what we find that I think is interesting is that, you know, there's sort of a softening radius for the stellar distribution right around that radius, which coincides with where, you know, the gravity goes from, you know, it's gas dominated outside and presumably inside, but here they match. And so one of the ideas that we had that could explain this, maybe not, is that, you know, if the filament is moving to jiggle the stars out of that bottom, you know, where they're forming at the bottom in that ridgeline at the bottom of the gravitational potential well, we might have an analogous effect on the star cluster, and then have tidal effects and all kinds of things that are distorting this thing and helping to set the density profile of the star cluster itself, but also inflate the velocity fields. So maybe this will make it easier. If the gas is moving when they're forming, it might make it easier to then dissolve these things that we need to have to explain observations like we saw yesterday in Moody's talk, where these things are getting stripped apart. The only reason that's possible, I mean, part of the reason was the perturbation because of the galactic potential, but the other reason is that they're just not that tightly bound to begin with, right? Anyway, we can also look at the kinematics because we also have ideas about how things are moving. So these were all very static pictures that I showed you. So we can check out the kinematics in the gas. And for the stars, because we have this near infrared spectrograph since a long time, Apogee, the Apogee survey, so we can get a handle on the radial velocities of the different populations. So the grayscale is the gas. I think here we showed 13 CO, and then the blue points are the disk stars, and the red points are the velocities from ammonia observations, which pick out the protostars pretty well, and then we can start comparing these guys, and we can play a similar game as the position ridge line of the filament, but to find one in velocity and straighten out our filament and measure offsets in velocity from the gas that things should be forming in, right? And so that's what these things show. We collapse the whole filament, actually the whole cloud, and we show the velocities of the protostars relative to the ridgeline of the gas, and the velocities of the integral shaped filament disk stars, the young stars, relative to the gas. We can compare this, these things, we can estimate the kinetic energy, or anyway compare it to the potential, and these things, everything's bound. Obviously the protostars are bound, but also the stars are just not moving that fast, right? And then we can also compare the positional offsets and grab the velocities that we had before and calculate some time scales. So an important number, should have mentioned this. Does anybody know what a kilometer per second is equal to in parsecs per megayear? You get a chocolate?
I know the answer. Come on, someone else.
What?
Take a guess.
She got it. She gets the chocolate in the back of the room. 1. So keep it in mind, every time you're looking at numbers where people are comparing parsecs and kilometers per second, there's no conversion. It's just trivial. It's 1.
People in the middle, just beware. This is at the outer edge of my range. It may fall short. Ceiling out of the way.
Scattering.
I can get it.
Yeah, so anyway, we can use our spatial offsets and our velocities to calculate timescales, and then we can say, well, the integral shaped filament stars appear to be dynamically younger than the southern portion of Orion, which I'm not talking about too much here. It's not like a dramatic difference, but I think it's interesting. And we can also put these guys on position velocity diagrams. Those of us that work on gas are super used to these position velocity diagrams. But anyway, they're just phase-space diagrams, and anything you have a velocity for and a position for, you can stick on there. So we put the protostars, everything relative to the ridge lines, again, both in velocity and position, and the stars, little boxes are the same size in both diagrams. So you can see how puffed up these stars are relative to the protostars. And the axis ratios here, so one of the other points about a kilometer per second versus parsec per megayear is that, if we have our things in these units, then the slope encodes a time scale, right? So it's useful to keep in mind. You can calculate just sitting there in audience slopes, you can get a time scales and then grill the speaker and what's happening with these time scales. So in this case, you have super short time scales for these things, so we know they're dynamically cold, they're glued to the filament. In these cases, time scales are longer, and we just calculated them. So the axes are order 1 million years. Anyway, we just calculated them, they're about 0.44. And so this is this puffing up effect. There's a lot of different ideas for why this would happen. And the one we came up with was maybe a little bit, I don't know. Anyway, we thought, well, the protostars are forming on the filament at the bottom of the potential well, so maybe to puff up the velocity field, the filament has to be moving so that the protostars can inherit that velocity and become, they can inherit that velocity and become puffed up by the time they get to the disk phase, the class 2 phase. And then there's like a major, humongous elephant in the room. Well, one thing is that, this filament actually looks like a wave. And we're like, maybe it's a wave, right? But then why would it be moving? Right? I just showed you, it's like this humongously massive thing. Why would it be moving? How can we generate, force on this thing? And we're not totally sure, but So before getting to that question, maybe I should say that I told you Orion was an H2 region, so maybe in some way, shape, or form, you could imagine a way of blaming feedback for this, right? As these massive stars and stuff's happening in there and all that. But we saw in Johnny's talk already that even in these sort of garden variety, lower mass film, everything is forming on the filament ridge lines. even in regions where there is no feedback, and even in massive clouds. So this is an example of Rodrigo's work in California. I'm not going to get into the main result, but anyway, California is as massive as Orion, but thought to be in an earlier stage of evolution. So it doesn't have the same concentration of dense gas mass, and it has really a meager fraction of star formation rate as Orion, but it's the same mass scale, and everything's forming on the filaments. So this is the ridge line in the region we looked at, and these are the stars overlapping with the ridge line. Everything's always forming on the filaments, so you got to get things out of these filaments, right? And so we, maybe foolhardily, but anyway, propose that perhaps the magnetic field could be playing a role. There's some previously interesting results, and they go back and forth. Maybe the field's helical, maybe there's some perturbation, we don't know. But anyway, there's only two forces that we could plausibly look at in the system. So on some level, we felt we had to deal with it, right? And I'm not going to get into all the ideas about that because I want to say a little bit about the other ideas about what could be happening. And so, one is, how do you inflate the velocity field of things? I think Nuria showed an example of a simulation by Matthew Bates. And so a lot of times people just think, well, you inflate the velocity field by inheriting it from the gas. If everything's collapsing from large scales and coming in, and then you can get the velocity dispersions in the stars that you need. So this is like a cold collapse-like scenario. But we don't see this distributed mode where everything's kind of like, collapsing from, everything's always on the filaments, right? Everything starts out cold. So I'm a little skeptical of this, but I think it has a lot of merit, maybe in lower mass regions, like Taurus or something like this, although Taurus also has prominent filaments. But anyway, I think it's a valid idea to test out. I'm just not sure that it applies to something like Orion or higher mass scales of clouds and protocluster formation. Another idea is gravity. Duh. Why go, into complex, MHD stuff if you can just explain things with gravity? Now, the basic idea here, so this is N2H+. And Mark talked about N2H+. N2H+ is an interesting tracer, and I'll tell you guys about it a little more in a minute. But anyway, the main thing is that traces dense gas. So we would ask if we were paying attention to Mark, what's the critical density? Order 10 to the 4. Forget the exact number. But it's doing better than CO. CO has a lower critical density. Anyway, these guys, Alvaro Acar and collaborators, observed Orion with IRAM. I think these are IRAM data. And they saw this feature, this sort of like blue shift, right? And so if you have, your cluster in the foreground, so you guys are the audience, clusters here, the filaments here, and it's infalling, you should get blue shifted gas, and that was exactly their interpretation. And I think it's really reasonable if you don't know where the cluster is relative to the gas filament. But Gaia data is giving us some 3D information on this, and this is just one example where we can show the bin Gaia parallaxes. Why did we bin? Because the parallaxes for Gaia aren't that good. So we want to beat down the noise a little bit. So I think we took 50 YSOs per bin. So they're a constant number per bin. Each point is a parallax bin. And we see this wiggle. And basically it's what Tom summarized in his review article, that the ONC is more distant than the filament. So then the interpretation of this would be something more like outflowing. This is a problem, right? If we think we know the geometry of the system, what's going on with this feature? We don't really totally have a good answer. It's a little hard to see the wiggle in this diagram, but we can stretch it out a little bit. And the other thing about this that's that we noticed, basically, so the green stuff in the background, so these are the Gaia parallaxes, the green stuff in the background is that N2H+ gas, that dense gas I told you guys about. So what kind of system has the positions correlated with the velocities in this way? You guys remember, like, undergrad physics lab? anyway, if we
Particularly captures.
if we want to report on this, you know, in a relatively straightforward way, we'd say it's a standing wave. So we're coming back to this idea that this filament could be moving, but how you get a standing wave, you know, in this, at the end of this GMC, I don't know. But anyway, these are the constraints from the data. And this is one idea. There's a lot of other ideas, like I just told you. So-
I'm confused. So these are Gaia objects, no? So they are like already seen in the optical and they follow very well the gas. But then in your previous plots, you show that the
Excellent
the
question.
class 2s are more like spread.
Yeah, I didn't give you all the information.
Uh-huh.
Let me go back to the map. Actually, this one's good. Whoop. This one's good enough. We selected a small distance from the ridgeline to try to get at somewhere closer to where the gas is, right? Now, it's a fair point. So what do you think you're looking at here? If the gas is like super dense, maybe you're selecting preferentially foreground objects, all this stuff. And I think it's possible, but it seems really unlikely. I'm not a big believer in coincidence, I guess. So it comes down to belief. But anyway, there could be many problems with these data, but the correlation between the positions and the gas velocities seems very hard to mimic all along the filament via some like observational selection effect, given that these two, I mean, this is Nobayama, I don't know, from Tatematsu, I forget the year. It's a, you know, these are completely independent data sets. Like he took the data, analyzed it, published it, made it public, and then 10 years later someone launched Gaia. You know, so it's hard to reconcile that. But it's a fair point. Could be some selection effects here.
So besides this correlated point, there is also this background of many other objects that would be...
Yeah, so we wanted to trace that ridge line as best we could to see if we could get at some three-dimensional structure of the cloud. Now, other people have done this, but they haven't focused on this filament in particular in as much detail, actually, and Nuria showed some of that, but Marina Kunko, etc., have gotten the basic geometry of the system of RNA as a whole from Gaia data, and the subclusters and all this other stuff.
Rotation. Kind of be some kind of superposition
like-
rotation of the original gas parcel or so.
Yeah, so we don't see velocity gradients perpendicular to the filament ridgeline. But obviously we have some, you know, red shifted and blue shifted portions along it. So do you think the filament could be like tumbling?
Something like that.
Yeah, I don't know. But, you know, it's difficult to interpret these kinematics, right? So, anyway, I feel like I'm taking a really long time. Anyway, this N2H plus dense gas tracer is interesting because it functions like if we could just strip off all the flesh and look at the skeleton, if we're interested in the skeleton of you know, the human anatomy. And so it's this kind of 3D filter, and it picks out the higher density stuff. If we want to see the gas that's more closely related to the star formation process. So I'm going to just give a very brief OMI-EMF kind of unsatisfactory summary. We select these protoclusters. They're compact. So the masses don't look super impressive compared to 10 to the 5 in Orion, but actually they're more compact, right? So you're packing in more mass per unit volume, right? And then these protoclusters are coming out. Common thing in astronomy, obviously, is like you have some galaxy-wide survey, in this case Atlas Gal, and you pick out, you know, the interesting clumps from that, and you know, design your experiment to match whatever. But anyway, so this is Atlas Gal selected, and the interesting thing, I think the thing that makes SARFORM different is just that it's matched resolutions. We have factors of order like 3, no, not quite, maybe 2-ish, in distance variation in our Berto clusters. Since it's an interferometer, we can tune our angular resolution, and so they're at matched resolution and matched sensitivity. Observed that way by definition, so the results in the different protoclusters are intercomparable in a way that traditionally we haven't really had this type of experiment in star formation. We just have to let go with whatever sensitivity we have and then know that we're just detecting high mass things and things that are far away and getting everything in nearby, and everything's biased. So we hopefully have at least tried to address that problem here. This just talks about the selection. Here's a table. You know, you really want to pay attention to the sizes and mass scales in units of 10 to the 3, so that gives you an idea. And here's this sort of alphabet soup that strikes fear in our hearts, or at least mine. This is complicated, right? These are all the lines that we get, and so we don't really care. We just want to focus on a few and use them for evolutionary diagnostics. In this case, I already told you guys about N2H+. If you want to be really nerdy at a bar, remember that it's called diazenylium. Anyway, this one I can never remember what it's called, so I just call it CH38 in good Spanglish. And it's a first order temperature estimator. Anyway, blah, 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 this and that, outflows, shocks, it's all super cool. H41 alpha is an indicator of H2 region. So that's really what we want to make some link to the title of this talk. What I want to do actually is not get into the details, but just tell you guys that you need to talk to him about H41 alpha. So it traces, you know, these H2 regions, and it's kind of like, you know, your trash is my treasure type thing, right? Where we want to use it to decontaminate the continuum of free emission, but we can also use it to, you know, to study the properties of the H2 regions, electron density, ionizing photon rates, etc. They're also very important for these protoclusters. Anyway, we can use this H41 alpha along with the continuum to put these things on like an evolutionary diagnostic, and this is what it looks like, but we don't know the time scales. We don't know what's going on here. But it's sort of like a, quote, feedback-based metric where we can rank our things, very little, H41 alpha emission, and much more. And we call it evolution. And this is where I want to talk a little bit about the N2H+. So we have these are the moment 1 maps, so the velocity field in the dense gas for all the protoclusters 2 are missing. And actually this is an important part of Rodrigo's thesis work, so I encourage you to talk to him. I don't want to get into it too much, but we talked a little bit about position velocity diagrams in the dense gas, and so this is an example of his work. One of the things that we see is that, so these little pink things are the cores, these cores. And, you know, they have these, it looks like they have these flows going towards them, but we also don't know if maybe there are things going away, just like the degeneracy in Orion, right? But we think, because of various things that we've checked, that it's an indicator of inflow towards cores, and I should note that the pink points are independent velocities. We're obviously not sticking them in based on the N2H+, that would be crazy. So it's a different tracer that's higher density and a little hotter. You see it. Anyway, and since we remember the Orion part of the talk, we can also put a little time scale arrow on there, right? So that we can interpret what these PD diagrams might mean. And the cores. I think I'm going to stop here. But I want to highlight that we have cool outflows, and we can take the cores and separate them based on the outflows as signpost to star formation between star forming and non-star forming, and try to get at the mass distribution just like we did for stars in the IMF, and then we can compare the slopes, etc. So I think this is accepted and already out and all that. I forgot to update that. So it's good to check out some outflows in Orion. And aside from JWST, which is like the obvious, like cool thing, to get at more extreme environments with maybe lower star formation efficiencies, protoclusters like this, where we can't even see the class 2 disk population, I just want to mention the local volume mapper, very, very briefly. I don't really work directly on these data, but local volume mapper is part of SDSS 5, and it's going to get this sort of feedback type data that we need to also be able to be put on similar ground to be able to talk better to the extragalactic people. So that's one aspect of this, and the other aspect is that it's, I think, going to do a good job at addressing those two dirty words that we don't like but we have to deal with, which is subgrade physics, in terms of feedbacks. Maybe finally we can get rid of this notion that we have of, like, quote, the magic of feedback by getting these optical IFU metrics in all of the galactic plane and some nearby systems like Orion. And so they just started observing. So I think it's going to be something to look forward to in the future. Anyway, thank you.
All right, we do have time for some questions.
So going back to, just going back to your point about filaments oscillating, can I just ask, do you think turbulence would play a role in that, or like the turbulent, different turbulent modes? I was just wondering about that because you haven't mentioned that factor. Like we could talk about gravity or maybe something else. Would that play a role in the velocity dispersion and dragging out the velocity field?
Yeah, so I think that's a good idea, and I think other people actually already proposed this, like Padawan and stuff, that the stars are inheriting elevated velocities.
I remember reading something about
But our protostars are already cold, and they should have been affected by the turbulence. They're already kinematically cold and already glued down there at the bottom of the filament. So it doesn't seem like they don't have the velocities already compared to the disk stars, which are puffier.
Right.
So I don't think that, I think that's potentially a source, or could have been a good idea for a source of like elevating velocity fields, but I don't think it actually works, actually, because when we look at the N2H plus gas, it's also kinematically cold. That's why the protostars are kinematically cold. So now, I think in that case, maybe, at least in that conception, I don't think it's turbulence in that way, but maybe there's some larger scale thing that's happening where you're gonna, perturb the filament in some way, so you get these larger scale things, maybe.
Because you're talking about standing waves too. I mean, you think about it as some spring, somehow in one end it's being perturbed by some sort of external forces, and whatever that it could be, and could that play a role too? Or if it's just so embedded, or if it's already so embedded in deep in the potential that no matter what's going on one end of the filament, nothing's going to really shake it in that sense. Because it's not really a string, I get it.
I think that it has an anchor on one end, which is this huge L1641 cloud that actually dominates in the mass. And then there's a perturbation traveling through. That would be the idea on some level. But we don't really know where this comes from, and we've appealed to quote something with the magnetic fields. But it's not, it's not satisfactory even to me. And it's much less satisfactory to a large portion of the field that doesn't want to deal with magnetic fields at all. You know what I mean? So they're like, no, you don't get away with that magic. But I think it bears looking at. Anyway, I'm not answering your question, sorry, but we don't have a good answer. We have data that are hard to explain.
Yeah. Okay.
Other questions?
In these sort of Bonnell-like simulations, the older zinc particles sort of bounce back from the denser gas and disperse, whereas the recently formed zinc particles are obviously more correlated with the dense gas. So qualitatively, that looks like the observations. No, and I'm not saying those simulations are correct, but I didn't get what's exactly the problem with them. I mean, I know, for example, they don't follow the n-body accurately, you know, by principle, you know. But,
No, it's when you look at them, it's true that the younger single particles are correlated with the gas, but the gas is in these little chunks on large scales infalling. So that when you can build up the velocity field of the older component. And we don't have things forming everywhere. We have things forming on a filament, cold. So we can't appeal to that explanation to inflate the velocity field of the class 2s. Is my basic interpretation. The other thing about I don't want to pick on Bate because I think his work might be good for lower mass molecular cloud, something like this, but the mass scale of the simulations are low. It's hard to run, you know, things like we have an OMIMF and even Orion level masses. It's not a trivial numerical exercise, but what often happens is that people run a low mass system as an example for the high mass systems, and I think we have to be wary and follow Mark and always ask, what is the mass scale that we're dealing with, observationally or in simulation, whatever, always. Does that make sense?
yeah.
Other questions? All right, well, I look at the clock and I see it is exactly time for coffee break, so I declare coffee break until noon.
Lo siguen buscando y yo lo he hecho buscando en el chat y poniendo puntos.
But if you need to, can you just get a handle on what the velocity is?
Lo habrá cuadrado así, tío. Pero joder. Pero no sé, hoy. Yo no creo que supere.
So the velocity dispersion of the class 2 population, is that coupled with the velocity of the gas that you see in the film? So when you're showing the standard wave.
No, there's right. So the velocities of the gas correlated with the positions of class 2. Okay. So we use the stars as a signpost for the positional, like, you know, the filament. And then we have the radial velocities coming up, and we happen on top of each other. You see what I'm saying? Yeah. So we saw this correlation, and then the reason that's where you'll find that. Okay, it was rejected, but I think it's a cool one.
Because one of my thoughts was if you're getting a high population of multiple systems forming early in peristaltic evolution, and then those multiple systems don't end up stable, and then that ejection of protostars forming based on unstable systems can contribute to that. But there's that correlation with how the gas is moving as well, and that doesn't.
It makes it hard to wiggle out of this one, actually, you know, and that's why I tried to separate out my whackable kind of field or whatever data. But I feel like we're not actually dealing with the computations.
I guess that's where it comes into everyone needs to talk to each other. I think everyone needs to be able to successfully deal with those computations.
that's really interesting. But I have a question. Maybe you said it and I missed it, but yes, sure. So my question, you mentioned that you think
Cristina. Hola, ¿qué tal? Buenos días. Vale, dime.
Sí, sí, estuvo hablando, sí, arriba ya está. Pero aquí lo solicite,
Vale.
sí, no sé si comentó ayer Alicia en la reunión.
Entiendo que tú, Alicia. ¿Cómo fueron los menús del... Sí. Espérate, voy a mirarlo yo que también lo he dicho. Que te lo he dicho con una calendar. Calendar. Diciembre. Sí, no tengo nada. Perfecto. A las 9:30. Pues si quieres a la 1. Venga. Pues, reunión con Cristina sobre... Déjame lo apunto aquí. Y directamente cogemos la hoja de cálculo y lo vamos... Cristina, tengo que entrar al auditorio que empiezan otra vez. Mándamelo, sí. Sí, y yo escribo a Carmen de Álvarez para reunirnos con el Sí, claro que claro.
That's amazing. I never had this idea that you, yeah, well, it makes sense.
Yeah.
Makes a lot of sense. Yeah. I owe you un piso. Para hacer. Perfecto, porque la foto es que casi no tengo dinero. Ayer te di todo el dinero que tengo.
Y me vuelve a echar.
Sí, todo.
We will resume, and this is Patrick.
Thank you, Mark, again. Right. So, in this lecture, I'm going to describe photostars and disks. So, I hope the lecture will be less formal than the previous one. I will be more on processes and try to relate as much as possible as introduced this morning. Right, so that's the plan I'm going to follow. First, I will start with simple scaling relations. Then I will discuss the formation of the photostars, aerostatic equilibrium, the first and the second collapse, and the formation of the group. And then discuss the process we have to, various processes we have to transport momentum in disks. So first start with consideration of quantum momentum. The alpha disk modeling, which is very still useful. The transport by gravity and magnetic field that I alluded to this morning, I will show some example. Discuss the self-gravitating disks. a little bit of MRI, and the Z zone and the new paradigm of this one. Okay, so first, I will start with some very generic considerations. And first with the statement. So you saw this complicated equation this morning that of course you have to know. But as I said, what is important is to have an intuition behind. And it's always very nice to describe your problem and understand it in very sequential degrees of complexity. Okay? So having a kind of extremely general and simplified view, and then several sort of refinements done to the very final one with all the processes, all the equations and so on, which is what I described today. Okay, but this is not in contradiction, and I think to develop an intuition, you really need to go, to go back and forth between extremely simple to extremely complicated and try to make the connections. Okay, so when we discuss collapsing clouds, there are a few numbers which are important to know, and just by very basic consideration, we can already understand a lot. So the very first number I would like to discuss is actually the ratio of thermal over gravitational energy. That's very simple. Huh? The thermal energy is essentially PV, so it's the pressure times in dimension times the volume, and this gravitational energy is Gm squared divided by A. So if you just replace the volumes here and the pressure, you can get this expression rho gamma R to the 3, R3 is to the 4, R3 is 1 over R, that gives you 4, and P is proportional to rho gamma. So you get that the ratio of these two terms is proportional to R to the 4 minus 3 gamma. Right? So if gamma is 1, say, so the gas is isothermal, you see that the ratio is proportional to the radius. So it means that as your cloud shrinks, the thermal energy decreases if gamma is 1. So it means that as the collapse proceeds, you have less and less support. So if the cloud is unstable initially, or slightly unstable, as the collapse proceeds, it will become more and more and more unstable continuously. And that suggests that essentially you get more and more fragmentation. And that's what we observe. There is a very important gamma that already appears here, which is the value 4/3, which is important. It comes from very simple magnet configurations, the ratio of thermal over gravitational energy, but it tells you that in 3D, in the spherical sort of configuration, if gamma is larger than 4/3, the ratio of thermal over gravitational energy increase if the radius decrease. And this is what happened in the sun. Okay, the sun is stable because its effective gamma is 5/3. Okay? So the sun is just having maybe grabo-acoustic oscillation, but it's not collapsing. So you have a very strong change of behavior when you reach this value. So that's something to keep in mind. It's something that will be important also later. Okay, then let's do the same with the centrifugal support. So the ratio of rotation over gravitational energy. So the kinetic energy for rotation is just r squared times omega, the velocity, the rotation velocity. And if you assume, it's a big if, okay, and the end of the lecture will all be about this assumption, but for the moment, let's assume this, that angular momentum is conserved. So this gives you r squared omega is a conserved quantity. So you can replace your omega here, r minus 2 coming in there, okay, and so when you combine these things, you find it's proportional to r minus 1. So it means that if angular momentum is conserved, as the radius of the cloud shrinks, the centrifugal support or the rotational energy just becomes enormous. So it means that you simply cannot undergo a very strong contraction, something like a collapse, without getting rid of most of your angular momentum, because there is what is called a centrifugal barrier, okay, which just prevents you from that. Okay, and then finally you can do the same again with the magnetic field. So the magnetic flux that we saw this morning is essentially B times A square. You take this magnetic over Gaussian energy ratio. If you assume that the flux is frozen, you can demonstrate that the ratio of this energy is actually constant. It does not depend on the radius. Which means that if the magnetic field is initially weak, it stays weak, and if it's strong, it stays strong. As long as the flux is conserved, meaning that you must have no, I mean, you must be in the context of ideal MHD, and you must have no generation of magnetic field like through a dynamo, for instance. Okay? So this very simple magnet consideration is at the base of the star formation regulated by magnetic field assumptions, which have been carried away in your time by people like Frank Shu or Primatos Moscovias. Because the idea that if the field was strong enough, it would block the collapse, and you have to go through a very slow process of leaking your flux to get star formation. So, just simple considerations, you already learn a lot. And they will guide, the intuition whenever you want to interpret complicated simulations. You can come back to those numbers. They will teach you, something. All right. Let's start with very simple equilibrium considerations. So, if you essentially consider an isothermal gas, which is a not bad description for the star, you can write the allostatic equilibrium, so thermal support equal to gravity essentially, and you can solve the equation. So you will find that's the radius of the function of density. You will find this profile, okay, where you have like a central plateau and then an envelope that you can demonstrate is proportional to R minus 2 asymptotically. Asymptotically, you find the isothermal sphere. And there are two important things here. The very first one is that this R minus 2 behavior means that you have no way to, or no easy way to actually define what the core boundary is, or what the reservoir of mass is. Because it keeps decreasing, but it never goes to zero. And what is even worse is if you compute the mass as a function of radius, r to the minus 2, if you multiply by instead the volume r to the 3, you find that the mass is proportional to the radius. Which means that the further you go, the larger the mass of your cloud. So that's the reason why those structures are extremely ill-defined, contrary to a star. Because a star has a gamma larger than 5/3, 4/3, equal to 5/3. If you do the same exercise for a star, you find that it really falls to zero at some stage. Really zero, mathematically. So a star is a bit very, for this reason, a star is a well-defined object. Most of its mass is in the center, and there is virtually no mass after some radius. Okay, so the star is a well-defined quantity for that reason. It's not the case for those clouds. Most of the mass is in the outskirts. All right. The second point is that, so typically what people have been doing is that they have set up by hand a boundary, okay, assuming that something outside confine the clouds. This something is supposed to be a pressure, so it can be, I don't know, WNM or something like this. Sometimes it can happen, but most cases it does not happen this way. And so most cases it's actually a sort of kinematic confinement or just just dynamical evolution. And so, nevertheless, people have been demonstrating that in the contrast between the inner density and the outer density is larger than this number of 6.4, you get an unstable equilibrium. So you can get an equilibrium, but if you let it evolve, essentially it quickly evolves towards a dynamical situation, so collapse. And only if the ratio is not smaller than like 6 or 6.4, then you get a stable situation. Okay. So the second step is to release these hydrostatic assumptions and look at what's happened during this collapse. So a nice way to do this, to avoid, to reduce a bit the complexity of partially differential equations that you solve in principles, is to use this self-similar ansatz, and this has been done historically quite a lot. So the idea is that you can express or construct those quantities like the radius divided by the time, density times the time to the square, and the velocity you just divide by sun speed. So those are normalized quantities, so dimensionless quantities. So it turns out that when you inject those quantities in your equation, and you have the field equation that I was been describing this morning, and you can just plug those quantities in your equation. Then you will realize that you can obtain a set of equations for which, for instance, only this derivative with respect to x appears. So this way, you can reduce the complexity of your system and have ordinary equations which depend only on these variables. So this is called a self-similar solution. And this has been used historically, for instance, by Larson and Benston, and also by Shu. And so this plays an important role because it allows you to catch some of the physics, not everything, but some of the physics for almost nothing or almost little. And so it's a nice way to dig into the problem. So that's the original Larson solution. So you have the velocity, it's before the collapse occurs. So the velocity goes to 0, and then asymptotically it goes to about 3 times the sun speed. The density essentially has a plateau and then r-2. And of course those self-similar solutions, they have a constant accretion rate, which is proportional to C S cubed divided by G times some value, some dimensional value. So no variable accretion rate, but nevertheless they get an entirely reasonable field. There is also this famous Shu solution that you probably have heard a couple of times, and which are still very useful. They are used in several codes because again they provide you a simple answer for very little. So the physics in this Shu solution is that you assume that you start with an r-2 singular atmosphere. You know the asymptotic form that we saw when we were solving the hydrostatic equilibrium. So it's highly unstable, and it starts. So initially it's completely at rest, and the velocity is 0. And then as you give a little bit of mass, which is initially in the center, you put a little bit in the star, so like you have been accreting. and then you create a small hole in your density field because you have moved a little bit of mass. And so the pressure is now dropping in the center. So the center is out of equilibrium. And so you start, because of this out of pressure center, you start accreting a little bit more because there is no support. And so you propagate. See, there is what is called a rarefaction waves, which propagates from the inside out, because the center is out of pressure, so a little bit of mass falls, and then, and so on. Okay, so you have this inside-out collapse, and the rarefaction waves, which propagate essentially at the sun speed, typically. Okay, so it's like you are hydrostatic, you destabilize a little bit the center, and so you start this accreting, okay, at the sun speed gently. Okay, so that's probably the less dynamical solution you can have from a star. It's probably not fully realistic, but you know, when you do model, you do mistake all the time. So the question is not being wrong or not. We are all wrong. Okay, always wrong. The question is whether we are sufficiently right for the model to be interesting. Okay, so this model is interesting for many aspects. So if it's sufficiently accurate for your purpose, well, then you should do it. All right. And so again, constant accretion rate. Okay, so that's essentially the isothermal situation with the simplest collapse. Of course, you can do more complicated things. People have been doing 1D numerical calculation for an isothermal collapse, paper by Foster and Chevalier. So they get a bit more, complications. For instance, you will get non-constant accretion rate, these sort of things. The next sort of degree of complexity comes from digging into the evolution of mass of the matter, and in particular these isothermal assumptions that needs to be relaxed. That's again, surprisingly enough, present in the Larson 69 paper, which was a very impressive piece of work. I think he had like decades of advance over many people. The paper is still relevant. So what's happened is up to this density here, okay, which is about 10 to the 9-ish vertical per centimeter minus 3. You are essentially isothermal because the dust is a fantastic temperature regulator. Okay, so it's really provide reasonable isothermal gas. But then, when you reach this density, what's happened is that the dust starts becoming opaque to its own radiations. Okay, just because the photons will be immediately reabsorbed, and so you are in the optically thick regime. So the cooling agent, so to speak, they cannot escape, so they are trapped. And so you enter an adiabatic phase, which is give rise to the so-called first Larson core or first hydrostatic core. So essentially, what happens is that the mass piles up, the pressure rises to resist the gravity, which is stronger and stronger, but collapse is not possible. So you just accumulate mass. And this will end when, again, microphysics will change. And the next change in microphysics is when the molecular hydrogen starts dissociating. So when the pressure increases and when the temperature reach about 1000-ish K, you start dissociating H2. And to do this, you need to pump energy into the surrounding medium. And it turns out it's quite a lot of energy because it's around 4.4 electron volts, which in terms of temperature, which corresponds to like 10 to the 4 K, it should be calculated, but I think it's 10 to the 4 K, even slightly more than that. And that's a pretty large temperature compared to the temperature at which dissociation starts, which is on the order of 2000 K. So it means that you are pumping very efficiently energy, and so it operates like a very efficient cooling. So this maintains the temperature at the floor of the order of 2000 K. And so this provides something like an effective gamma, which is on the order of 1.2. Importantly, it's below 5. It's below 4/3. 4/3, if you remember, is the critical index for it. So it means we are back to a situation which is unstable. So if you accumulate enough mass, the collapse just restarts. And so this is what happened. You see that in this plot from Larsen 69. You have the density, at low density you have this R-2-ish envelope and velocity which increase, so it's swimming in collapse. And then you see at some stage you find a big decrease of the velocity and the change in the slope. This is signing the presence of the first hydrostatic core, which is adiabatic. And then you restart the collapse, so you see the velocity re-increases, and you again find something like an R-2 slope. And this finally ends when the gas becomes again optically thick, but this time not due to the dust, but because of essentially the atomic and proton opacity, essentially. So this is this time the second collapse, and the photons again cannot escape, but we are not discussing this time, say, infrared photons, but really visible area. I mean, we are building a protostar, which is optically thick to its addiction. It's a perfect gravity. So it cools only from on the surface, but very inefficient. Okay, so that's the information of the protostar. So that's essentially the story of an isolated collapsing piece of cloud, which is not rotating. Isothermal phase, R-2 types of density profile, either shoe-type very gentle solution or more violently like Larsen-Penstone, it depends on the initial conditions. Then end of the first isothermal phase, formation of a first hydrostatic core. The mass of this object is typically 2, 3, 10 to the minus 2 solar mass. So you accumulate 2 or 3 10 to the minus 2 solar mass. Essentially you are hydrostatic during this phase. Then dissociate H2. So collapse restarts. Okay, so you get another 5 orders of magnitudes in density enhancement. And then you become really opaque to the optical partitions, and that's the end of up to the next collapse would be when there is no more nuclear energy fuel, and then it will collapse, as you know, in a compact object. But that's a different story. Yeah.
So I'm more observational towards this very cool thing to see, but this Larsen core, is it something that you can't observe the Larsen core, right? It just
there is a hunt for Larsen core. I'm not sure it's a very convincing candidate. I don't know, Ali, whether you have.
I think they're hard to identify, and people don't know exactly what they're looking at. But there's a few candidates in nearby regions that are closer.
Very cool.
That maybe, what's that?
Yeah, that said, the number of claimed actions larceny first occurs in the literature
Yeah, violate.
exceeds any plausible estimate of the number that actually exists.
Well-
So, you know, there are clearly more claims in the literature than could possibly be
Yeah,
there.
but not all the candidates are not actually, cannot plausibly be based on like crime arguments and so on.
Yeah.
I think they're hard to observe. So I would take it with a grain of salt if somebody reports a candidate, or it could be something super interesting.
So this is like something GWST regulation would help with potentially?
Well, DWST's tracing, I think, generally hotter
Okay.
temperatures,
So you would be able to see.
for the most part. So if you think about like Velos, a very low luminosity protostars that Spencer discovered, you know, it's already longer wavelengths.
Got it.
And they had quite some trouble disentangling what those were. They were grab bag in the end.
Yeah, I mean, their age is short, it's supposed to be on the order of 1,000 years, that's why they are so few. But when you have rotation, things become a bit more messy, and they could live, I mean, they probably become the early disk. And then the age becomes not so easy to estimate because some of it survive, they not, you know, collapse like very simply because you get a stellar plus disk structures, and some of the material may be part of the disks. So the age of 10 to the 4 years has been claimed. That's why they be more. So yeah, I mean, there are difficulties of that kind. Right. So yes. So finally, I would like to discuss a little bit formation in the group. So all of that, of course, is important, and in your you know, building of an intuition, of understanding of a problem, it's starting from really the order of magnitudes, then some simple solutions, and then finally with the full complexity. But all of that is important to really. But so one of the final states is this one, so where you start with turbulent clouds, where you see those filaments forming by a combination of gravity and turbulence. And so the points are the star. And at the end you see the feedback kicking in, so it leaves you with a cluster that may survive for a while, and part of the stars, you know, they just they are not pushed themselves by the feedback. It's more that the feedback is actually pushing, that's H2 regions in this case, is pushing some gas, making it unbound, but this guy is still forming some stars. Right, so you see it's a complicated story, but that's typically where we're going to be. And well, I was just discussing at coffee break with Noya about dissolving of clusters and these things. So there's a little bit of this, but what you want to do is very difficult. So, yeah.
I was just curious what the mass is in the box at the beginning, in the gas.
The gas, that's a 10 to the 4 solar mass clamp in this case. Yeah. So, yeah, so at the end of the day, all of those collapse that I was describing will occur in, around all of these regions. Plus, of course, a lot of complexity induced by the non-sphericity of the medium and the rotation. So that's what I'm coming now. Okay, so let's re-simplify the problem. Of course, we reach toward the realm of those very difficult simulation where it's difficult to track exactly what's going on because of it's a mess. And first, I would like to ask a simple question. What is angular momentum? It sounds silly now. It's easy to know. What's angular momentum? Just rotation. Well, and what does it mean? Conservation of angular momentum. So if I ask you the question, the provocative question, is angular momentum conserved? Who wants to answer that question? It's a two chocolate question.
We're running low on time. They're not in front of us delivery. In fact, they're exactly 2 chocolates.
Okay, stop that. So, because we can hold our promise. Let's try to answer the question ourselves. So, easy, yeah, the angular momentum, you know, it's the sum of the velocity times the position. Easy. Okay. Is it conserved? Well, yes, of course. I mean, if your center of mass is this point O, you can easily demonstrate that the angular momentum with this definition and with respect to the center of mass is a conserved quantity. That's easy. Next question. Is the center of mass the relevant point to consider in the system? Do we care at all of the center of mass? Well, it depends. If you have a well-established star which dominates the mass and with a tiny disk around, okay, you may say the center of the star is the center of mass, and the angular momentum with respect to the center of mass is a conserved quantity. But if you are in the process of assembling your mass and you don't know where your star is forming, if you are dealing with a situation that is not axisymmetric, so if you have a little bit of mass there, a little bit of mass there, you know, like a patatoid, the center of mass is completely irrelevant. Actually, you can see that if there is a trend in the system, is to collapse around the center, where the potential is minimum. And the potential is not minimum where there is at the position of the center of mass, because of the 1/r dependence of the potential. So the system is not going to collapse toward the center of mass. It's going to collapse to another point. And this point, generally speaking, is going to move with respect to the center of mass. So in these conditions, angular momentum is not a conserved quantity. You can demonstrate, actually, that the derivative of the angular momentum with respect to this point C, which is not your center of mass, is actually given by this. So is the distance from G, where G is the center of mass, times the acceleration with respect to this center. So this means that in a collapsing core, it's totally unclear that the momentum is something inherited, or which has to be inherited from the large scales. I'm not saying it cannot be the case, I'm saying that it need to be the case. And actually, we ran a numerical experiment in this paper, where we started with a core, which is non-axisymmetric, and completely at rest. Zero velocity, meaning zero angular momentum. And guess what? We form a disk. Okay, so and we are very careful about conserving angular momentum, the error, and blah blah blah. And that can be understood very simple. Angular momentum in this context, more generally with respect to a point that is not the center of mass, is not a conserved quantity. There are something like an inertial torque. Okay, so of course people like me who do theory are probably guilty of this, meaning simplifying the problems as much as they could, and so many theoretical studies have considered an axisymmetric situation where you have some rotation and some axisymmetric problems to make it simple, and I think it was worth to do so. But it induces this idea that you can distinguish easily between collapse and rotation. It's not as simple as that. You get a mixture between collapse and rotation, and at some stage, something far away you would call it collapse, and as this approach your protostar more and more, you see the sort of you will interpret this motion more and more like rotation. So the distinction in the general case is not easy, and the notion of angular momentum being simply inherited from the larger space is also something which is not straightforward at all. Okay. Actually, there are some observations going along this line that you start seeing things that you would interpret as observation, which sometimes are counter-rotative or completely misaligned with the disk that you see on the small scale. All right. Okay, next questions. So assume that we are now in the nice framework of an axisymmetric system where angular momentum is conserved because the center of mass and the collapse center are the same. Okay, why do we need to lose angular momentum? So if I just consider a very simple-minded system, which is so you have a central object, like this, and then you have two rings, G1 and G2, sorry, carrying an angular momentum. So let's assume that this one, G1 is smaller than G2 because it's closer to the star. So you can simply assume that gravity is equal to the centrifugal force, which gives you a relation between the radius R1 and G1, the angular momentum. So you can work out the total energy of the system. So the total energy of the system is the gravitational energy of the mass located at R1 plus the kinetic energy of the rotation. So you can use that relations and then you obtain this relation, this energy for the mass M1. And you do the same for the mass M2, so you can add them together. Okay, so you have M1 over G1 squared plus M2 over G2 squared. That's the total mass of your system. And so then you are asking yourself the question, well, what's happened if I transfer some mass between my ring 1 to my ring 2? How is it energetically favorable for the system? Okay, so we say, okay, I transform M1 in M1 prime, so I add a little bit of mass to my inner ring, and I remove this mass from my outer ring. Okay, but to summarize, I have my two rotating rings in equilibrium. I take a little bit of mass of ring 2, and I give it to ring 1. And I look how the energy of the system evolves globally. Okay? So those are not very difficult mass, but at the end you can see that the final energy, Et prime, is equal to Et, the initial energy, minus the quantity which is positive because G1 is smaller than G. And so it means that in this process of moving the mass from 2 to 1, I bring the system into a lower energy state, which means more favorable. So this is the clue of why you would transport angular momentum. Okay? As you move the mass, leaving the angular momentum outside for equilibrium. Okay? As I move the mass inwards, I'm bringing my system into a lower energy state. So if I dissipate the energy that I've been using in the process, I cannot go back. I'm trapped because I don't have energy to do anymore. Okay? So it's irreversible. So that's why those systems tend to evolve in that direction. It's energetically more favorable. Okay? You can ask yourself the same questions, but this time you leave the mass where it is and you move the angular momentum, say from inside to outside. Okay? And so when you do this, you find the same thing. This time it's energetically favorable to move angular momentum outwards. So those systems, they will, if they can do it, they will do it. So moving mass inwards, angular momentum outwards. It's a general trend, just from simple energetic considerations. Then of course it doesn't tell you how you do it and in which time scale. So that's where you really need to know the detail of the system and go through all the possible mechanisms. but the general trend is this one. Okay. So, before we digging into the various possible mechanisms, just some general consideration on disks. So those objects, the photoplanetary disks, they have been seen for decades now. So the size, you may be seeing smaller guys now, but say 100 AU, typically, the mass can be 10 to the minus 2 solar mass. The lifetime that you can estimate from the companion stars is like 1 million years, or few million years. They have an equation rate in the order of 10 to the minus 10 to the minus 8, the distribution. They are thought to be in Kepler rotation. Okay, so because of this age, we see that those objects disappear, and so we needed to quickly understand how equation is possible. So the first calculation that people have been doing is the diffusion time scale. So relying on the viscosity, as I was mentioning this morning, you can transport angular momentum just by viscosity. So you know the molecular viscosity, and if you just construct the time scales, taking the typical size of the system and the viscosity which comes from essentially the product of the sun speed by the collision time, you can work this out and you find that the time you will need to transport angular momentum is on the order of 10 to the 12th year, which is simply 6 orders of magnitude larger than the million years which is in for disks. So there is no way that the molecular viscosity can be the source of transport. Is far too low. So people have been introducing this concept of anomalous transport, which initially was seen or thought as probably a sign of turbulent viscosity. So you can work out a general model, which is called an alpha model. So essentially the idea is that you will have larger scale eddies that will be responsible of the transport. So you construct a bit by hand the viscosity, which is the product of a typical size by velocity. And then if you do some kind of reverse engineering, so you know what the time scale, you say, okay, I need to have my angular momentum being transported on that side. I need to have an alpha of 10 to the minus 2, where alpha is the dimensionless number that you will put in front of the viscosity that you have constructed by hand, so the thickness of your disk times the sun speed essentially. And you say, okay, this comes from some process. And this something has to be on the order of 10 to the minus 2 if I want to explain the lifetime of the disk. Okay? So at this stage, no physics really, the detail of the process. It turns out that this approach offers you a way, say, to model the evolution of those objects. Once you have prescribed an alpha, you can work out equations that I'm describing here. So this is the disk. You make essentially the balance. You will make a mass balance and a momentum balance between the air and air plus the air. So this will bring you the continuity equations for the column density, okay, which is more or less identical to the density equation we discussed this morning. And you will also obtain conservation of angular momentum Again, it's very similar to what we had this morning. Okay, this is column density and grammar momentum. So column density times L times omega is the velocity times L is the momentum. Okay, this is the advection of the momentum. And you have a torque which comes from this, alpha viscosity. So you assume that you have like an effective big viscosity, and it provides you a way to communicate your momentum between two layers. Okay, so that gives you a torque which can transport the momentum. So when you combine those two equations, you can obtain a diffusion equations for your column densities. So the velocity essentially has disappeared, and you get the equation which is describing the evolution of the column density. So this is something which has been used in the old time when it's called the Pringle forget the name of the others, but so that they have these Dirac functions or Dirac distribution. They were studying how it spreads, how the ring initially spreads around your star. And so essentially this was the most educated way to calculate the evolution of my two rings, and they would also show that the mass tends to concentrate in the center, and the momentum will be expelled out of the system through essentially the diffusion of a tiny amount of mass. Okay, most of the mass will concentrate, and then you bring at larger and larger distance a little amount of mass that will carry away your angular momentum. So this is still in use in sort of models. For instance, people that try to understand our solar system, they rely on this sort of modeling. So again, if it's useful for you, why not using it? Of course, the whole issue is the viscosity and this alpha prescription that needs to be done. Okay. So let's now dig into the detail of the processes. So if you remember this morning, I was discussing this equation. So here we have actually three candidates to transfer angular momentum. One is here, and actually there are two ways associated to this one. One is just the advections, so the radial velocity, but you also can have like turbulence, where you have like stochastic flux which goes back and forth, but which on average will have a contribution, net contribution of accretions. Okay. Then you have here this magnetic braking terms that I was describing, and here you have gravity, which, if you remember, can work very efficiently if you are non-axis symmetric. So let's see how this kind operates. So this is the formation, this is the collapse of a core, and that's the zoom. Okay, and so here you see the rotationally driven sort of spiral waves which develop. You see the two axis symmetry, and you see the system. Most of the mass has been concentrating here. Some of angular momentum is trapped there, and you have the partial spiral wave. So you have the gravity in action here with all this symmetry breaking and the spiral patterns. And if you see this, like face on, and see all the dynamics occurs really in the equator. If you do the same thing, but this time with a magnetic field, okay, you see a completely different story. Okay, all this complicated dynamics is gone. You have like a central object, small remaining spiral patterns, but really small. And it's like everything is simple, and the angular momentum is completely gone. If you look again at the same thing but this time phasor, okay, you see this time you generate this outflow. Okay. So what's happened here is that you have twisted the field lines very heavily. So on so initially the field lines were straight, you just compress them through gravity, essentially. That generates this machine, and then you wrap them around by rotation. And so here, if you think back to these equations, B phi times B, okay, B phi is the toroidal field, and then if you have some Bz, for instance, you will have Bz times B phi, so you have a torque which allows you to transport angular momentum along the magnetic field, along the Z component of the magnetic field. So you can see almost these connections. Those field lines have B's, phi, and Bz. So Bz times B phi gives you a flux of angular momentum in that direction. So that's what happens in the system. All your angular momentum is transported away. Okay. And so it allows you to get rid of most of your angular momentum. Okay. Of course, this simulation is assuming ideal energy, but numerical energy, because of course numerics will introduce sort of numerical diffusion, so it will not be as simple as that. But say at first sight, it will be ideal energy, and as we mentioned this morning, and this may be a pure approximation. So part of the effort nowadays is to take into account properly the non-ideal processes, alpha diffusion, omit distillation, and all effects. Okay. So let's have a look now to the self-gravity disks and this important concept of the two-way parameter. So you have rotating disks, and you can pick up a little fluid element here, okay? And you can work out the thermal energy, which is just the mass of this element, m sigma d square times c square. The rotation is just kinetic, so you take the differential rotations omega dr, that's the mass, and gravity g dm square over d. That's the sort of elementary energy of your field. It turns out just from that you can almost get the two multiplier, okay? Which otherwise you have to do, to get really the two multiplier from full set of equations. It's not an easy thing, but here you get it almost for a much more simplified way. So you say, okay, for my piece of fluid to be stable, I need to have either the thermal energy larger than gravitational energy, or the rotation energy larger than the gravitational energy. So the first conditions indicate that the radius of your piece of fluid element must be smaller than this quantity c squared divided by c Just say this has to be smaller than that. And you see, so this has to be smaller than that, and here there is a clear dependence, and not here. And the second conditions is that the rotation is larger than gravity, and here the trick is that dr square appears, while here you have only 1 over dr. So you have different behavior between those two. Okay, and so this time you find that the size must be larger than this value here. So now, if you want the system to be fully stable, you need to have no hole in the system. Okay? If this is an axis where you represent this size, dr, if it's smaller than this quantity, it is stable. If it's larger than this quantity, it is stable. But if in the if this guy is equal to this one, okay, then it means there is no unstable mode there. So the condition for stability is that this has to be equal to that. Okay, and this is the two-vertical. Okay, when you write that this radius is larger than this one, so this has to be there essentially, you obtain that the two-way criteria will be satisfied, so CS times omega divided by sigma T. So the true two-way criteria, actually, this is the epicyclic frequency, and this to get, you really have to perturb the equation and so on. It's trivial, but I mean to get a hint and a quick estimate, that's one way to do it. So the two-way criteria will give you a better nonlinear coefficient. Okay, so this turns out to be very useful to understand the evolution of self-rotating disks. Yeah, that's the full two-way criteria with the epicyclic frequency and the pi over there. So essentially, people have been running those self-rotating disks. You have a star in the center, and then you have a disk which is sufficiently massive for gravity to be important. Then they found that you get a sort of self-regulation. So it's like your system putting itself in a state which is close to Q on the order of 1. So it's a very nice prescription that you may want to use when you are doing some modeling, or even when you want to interpret observations and the thing. Usually it's not far from this. So the reason is the following. If initially the two-way criteria is very large, then the disk, well, it has to be, of course, viscously heated, otherwise the argument will not work. So if the heating comes from the viscosity, it means that there is no heating terms. So the disk will cool. So the sun speed decreases. So the sun speed decreases, then Q decreases. Okay, and so as Q decreases, the disk becomes unstable. So you start having shocks, spiral patterns, and so on. So that dissipates energy. So that heats the disks, and so CS will increase, and therefore Q will increase. So at the end, you always stay not far from the instability. So on the order of Q, Q on the order of. Okay. All right. So finally, I would like to mention the MRI. For a while, there have been, well, still there is an issue to understand exactly in a non-self-rotating disk how angular momentum is getting transferred. And if accretion is, so if gravity is too weak, you know what can transport angular momentum. And one mechanisms which have been proposed by a series of papers, I'm not sure who should be granted for that, probably the best is to cite everybody. Essentially, you have a disk with field lines on this, okay? And if your two fluid particles are connected to each other, what's happened is, if the analogy which helps to understand it, like you have two satellites orbiting around Earth, and they will be connected by a string. Okay? If you have a small instability, one is tilted a little bit, like this, okay? It starts moving more rapidly than the other one because of the Kepler orbit. And so it starts actually giving a momentum from the one that is in the closer to the star compared to the other one. So this exchange of angular momentum makes the one which is in the outskirts, to move even further away, and the one which is closer to move closer again. And so this is amplified, and that's an instability. So that's the essence of the MRI. So it has been, of course, it gave rise to many studies. So people have been looking at the pores of the mode, how they would develop, and how the flow eventually becomes turbulence. So this is a huge literature on that. And then more recently, people have been figuring out that the issue is that the flow, that the flow is not sufficiently coupled to the gas, meaning that the MHD, the method is not sufficiently high up. I mean, the atomic diffusion, molecular diffusion in particular, are too high, and so this dissipates the waves very too efficiently, and that's still the MRI. So that's still debated whether you could have some MRI there and so on, but it seems that the bulk of the disk may not be MRI. So the last paradigm which has evolved is similar to the simulation I've been showing you, that you have actually wind which are launched, and they may be carrying away the excess of angular momentum. So that seems to be for the moment the most promising paradigm. People that do study this, they do a sort of mixture between viscous and wind. So that's really where the field is. And I think I'm going to stop there. There are a few other mechanisms, but I think we don't need to discuss that. Okay, thank you for your attention.
I'm afraid we do not have time for questions, so just Maya to come up. Take the giant cocaine stick of destiny. All right. This is Maya.
Hello. Thank you for the introduction.
My introductions are very direct.
Yes. Yes, so my name is Maya, and it is not, in fact, Melanie, who was supposed to give this talk. So what I would talk to you about today is based on the slides that she prepared and she shared with me. So I'm hoping that I will do a good enough Melanie substitute. But if you have any questions at any point, please stop me and ask me. So I'm going to talk to you about feedback. This is the basic outline of this lecture. So first we're going to briefly talk about the importance of feedback. Then we're going to look into some degree of detail at the different stellar feedback mechanisms. And then very briefly touch on the impact of feedback on GMC scales and galactic scales, and finish with some questions. So, let's start with the importance of feedback. Well, this is a star formation school, so in preparation for our lectures, many of us did exactly this. We went to Google and then we searched for nice images to show to you guys. And the thing that happens when you look for star formation images is that you get a wall or something looking like this. And these are not exactly star formation images. These are really feedback images. If it wasn't for feedback, we wouldn't really be seeing very much of what's going on. It would just be some blob of gas with some stars somewhere in the middle, but nothing much to be seen.
So if nothing else, feedback is important for all these beautiful images that we already see. But this should really give you an idea that feedback is a very fundamental part of star formation. The moment we start having stars, we also kind of need to start talking about feedback. So in a more physically motivated way, feedback is important for the matter cycle in galaxies. So as cold gas is accreted onto a galactic disk, it goes into the diffuse interstellar medium, then under the effects of gravity, it collapses into molecular clouds, and of course, as we know, these then form stars. And as the stars are formed, they then fulfill the role of dispersing their natal environment. They return gas back to the diffuse medium, and the only other mechanism to disperse the clouds would be a dynamical one, and this could be important for maybe small clouds, but the really, really big ones, we do also need some feedback to disperse them. And then finally, through the galactic winds, which are also feedback related, some of this gas will leave the galaxy. So we have a cycle happening here. So, a few more points here. Without feedback, it would be, how should I say, we will be way, way, way further along the star formation process than we are right now. We will be pretty much done. The thing is that without feedback, we will have maybe some pre-existing turbulence, which dissipates on pretty short time scales. And then the cooling time of the gas is also relatively short, and then everything will just collapse, will form stars, just as we see in simulations that don't have feedback, where a lot of the material, pretty much all of the material that is contained in the clouds just collapses and forms stars. Done. I think we will be done with the star formation process. We will have in the past. But with feedback, sorry?
No school then.
Exactly. So, yeah, we're here. Oh yay, we're here, I don't know. So, with feedback, what happens is that the young stars inject energy and momentum into the gas, which limits or even reverts the collapse of this dense gas. And this is what is known as self-regulation. So, in a way, the more stars we form, the quicker we stop the formation of stars. So there is this balance happening between star formation and feedback. Here are a few side notes on feedback. So as it was already touched several times so far in the school, we have structure in the ISM, which means that stars are born in clustered environment. And also massive stars are the ones which are most important for feedback, as we're going to do now. But they live the shortest. So we have fast regulation of the star formation process, and these two things combined mean that the effects of feedback are correlated in space and time. They're not just randomly happening all over. Okay, so hopefully I've convinced you that star formation, feedback is important. So let's now look into the specific star formation, I'm sorry, I keep saying star formation, feedback mechanisms. So I heard that we're short on chocolates. However, I was thinking of posing this question to you. What type
build up a credit chart of chocolate.
There are a total of, well, there are 5 chocolates left. If you can come up with 5 feedback mechanisms, we can give that to chocolates and then just don't ask any more questions.
Consolidation, feedback, supernova, jets, solvents.
Oh, how about?
Yeah, I think that deserves a chocolate.
Yeah, but not going to be 5.
AGN is not to be the stellar feedback, right?
Yes, that's a good point. Thank you for clarifying. Yes, AGN is not something that we're going to be talking about, but the other one's pretty spot on. It is feedback, yes. And that is true. This was not like specifically enough stated.
Chocolate is also a form of feedback.
That is true. That is true. Excellent. Okay. More. More sources of feedback. There isn't that much more to be mentioned. We could maybe think of one or more too, but anything that anyone can think of that we did not cover already, which was maybe for the people on Zoom, do we have the microphone?
Oh my God.
They did not hear this lovely list of feedback.
Oh, I have the microphone.
Oh, yeah.
Oh, yes. I have the microphone, I just wasn't that fast. All right, repeat your list of feedback.
What? Okay, fine. Auto-ionization, supernova, stellar winds, jets, and I said AGN2 because
Okay.
it ends with a stellar word in there.
Awesome. Thank you.
Very complete.
All right.
Anything else that anyone else can think of? There is a chocolate and a cream. Yes.
Radiative feedback,
Yeah, she said photoionization, but
like direct radiative pressure.
yes, yes. I think this is for chocolate. Yeah, that's I believe everything I'm going to cover today, so we're good. Right, so here's the list. Outflows, those would include maybe some broader stellar winds, but also more collimated jets. We just heard about this, so this fits right into the previous topic. So the outflows will have the function of dispersing the natal cores of individual stars. Then we have non-ionizing radiation, which heats the gas, and it's also relevant for radiation pressure down here. We also heard about photoionization. So this creates the H2 regions that we're very familiar with. Then we also have stellar winds from high mass stars, which can create very hot, high pressure bubbles. Yeah, and down here in gray, it says cosmic rays. We're not going to be actually talking about cosmic rays. They are, of course, form of feedback. They are created in, oh, sorry, there was supernovae that I didn't mention somewhere. Yes, here. I was just going to mention supernovae now. So they're created in supernovae explosions. And in general, they have importance for the chemistry and the temperature of the ISM. But this is kind of more on a more global scale rather than like individual GMCs per star, for example. Right, so I'm gonna just dive into them one by one. First we have outflows. As we just heard, when we have the interaction between a star and a magnetized star and an accreting disk, we can also launch these bipolar outflows or collimated jets. You could in fact see some of them here in this image in the red color. For the untrained eye, it might be a little bit difficult to recognize them, but when you see them overlaid with CO contours, with the redshifted and the blue-shifted component of each outflow, then they become a lot more apparent. So we have these coming out perpendicular to the disk. And the jets could be really very collimated and just sticking out. So the outflows that we see here are important for generating turbulence and limiting collapse onto the individual cores. But typically we don't associate them with dispersing their entire GMC environment. And we don't believe that they can hold star formation on a GMC scale. If you're more interested in this topic, you should check out this really very comprehensive review. Apart from looking at this beautiful observation of outflows from stars, I'm also going to show you the simulation. Of course, all of these feedback mechanisms that I'm going to mention today have been implemented in numerical simulations as well. So here we see this bipolar cavity that is blown out from the outflow of an individual star-forming core. Typically, these are not so easy to simulate self-consistently because the outflows are launched from very small scales close to the star, but then the effects act on much larger scales, so we have quite a dynamic range. So next we go to non-ionizing radiation. So here we can have photons from, again, predominantly the ONV stars. They're going to come up over and over because, of course, they have higher luminosities and they're hotter, and so their feedback is just more significant to the environment. So the radiation coming from these stars is heating the material in the surrounding region to the photoelectric effect, and they are quite important for the thermal balance and the chemistry of their environment. But really the way that they would mostly impact the lethal cloud is through radiation pressure, and we're going to get back to that at the end. Next on my list is ionizing radiation. So as I mentioned, we all know about H2 regions, and I'm going to walk you through this brief schematic of what happens when we have ionizing radiation coming from high mass stars. So first of all, we have ionizing photons, so over 13.6 electron volts, the ones that can actually ionize hydrogen. And then we have a certain amount of ionizing photons that are emitted per unit time. If we have a fully sampled IMF in our mock cloud, which is just going to be a nice uniform density cloud, just as all of the clouds that exist in the universe, as we know. But if we have fully sampled IMF, then we have this ionized number of ionizing photons per unit time being proportional to the mass of the stellar cluster that we're forming in the middle. If we do not have fully sampled IMF, then we will have some stochasticity. So if our cloud is lucky or unlucky enough to have a high mass star, then it will get an H2 region. If not, yeah, that's what's going to happen for it. But here we have a fully sampled IMF, so nothing to worry about. So first we have, as I said, our little cluster in the middle. It starts to emit ionizing photons. And as this happens, of course, ionization occurs. But at the same time as hydrogen atoms are being ionized, we also have some recombinations that are happening. So some of the electrons that have been knocked out from the hydrogen atoms get recombined. And depending on whether or not they go all the way back to the ground level or to a higher energy level, they will also emit a photon. If the recombination happens all the way to the ground level, then this will be another ionizing photon, so all is good. We don't worry about the fact that the recombination has happened because we still have the same number of ionizing photons floating about. But if this recombination happens to a higher energy level, then the photon will have insufficient energy to further ionize another atom. So in that case, it's kind of like a lost photon. So in a sense, we keep producing these ionizing photons, but we also lose them to these recombinations that do not produce another ionizing photon. And because of that, at some point, we're going to reach an equilibrium state where all of the photons that we are losing through this recombination process are going to perfectly match the number of photons per unit time that our central cluster is emitting. And this will happen when we reach the so-called Stromberg radius. And over there, this is how it is expressed in terms of the number density of the gas the recombination coefficient and also the ionizing luminosity. And after we reach this equilibrium, we can't ionize further. So this will happen very rapidly. So we can't ionize further without dynamic changes in the system. But what happens is here we have gas that sits at 10 to the 4 Kelvin in an ambient medium of a lot less than that. So then we have a huge pressure gradient between the ionized region in there and the surrounding material. And this will drive a pressure-driven expansion of the H2 region. So, yeah, exactly that. And this pressure-driven expansion will, in principle, keep going for quite a while. Typically, it will reach at some point the end of the cloud, or just a lower density region into the cloud, and it will escape. It will be like a bubble that pops, if you want to have the imagery. So for the sake of being able to compare these feedback mechanisms later on, we're going to actually compute the timescale on which we would expect them, approximately, to disrupt the GMC. So in order to do that, this is how we model this expansion, the pressure-driven expansion that I told you about. This is a very, very classic problem that is quite well understood. This is the equation of motion for the expansion. What is really important here is that it's just driven by this pressure imbalance that I told you about. And this has a well-known solution by Spitzer, which is in this form. And we could rearrange this so that we could see at what point in time we will reach the size of our GNC. And then we have a time scale over which photoionization will be able to, in principle, destroy the cloud. Of course, this, as I said, was a very idealized situation. In reality, we have substructure within the cloud. So what will happen is that predominantly the lower density regions will be ionized, and then it will be really this kind of effect of popping a bubble, as I said. And then the ionizing material will be able to leave instead of being pressure confined inside the spherical cloud. But this is a level of approximation that we're going to take with all the feedback mechanisms for the sake of this.
Maya,
yes.
Can you give us a number, please, for this time scale? When you plug in typical numbers, what's the time scale? Are you doing that now?
It will come later.
Okay.
But yes, I mean, it depends on your conditions.
Yeah.
But let's say.
I'll wait.
Yes. Make a year-ish. Just to give you a more. Okay. Next on the list are stellar winds. Again, OB stars. They can drive these very fast and very hot winds, like we are talking really hot. So here in this observation, I believe this is 30 Dorados from the Large Magellanic Cloud, you can see X-ray emission from this very, very hot gas in blue. And yes, so these are very hot, very fast driven winds. They can also create shocks in their environment. In a way, you can see parallels between them and the H2 regions in the sense that you will have, again, a situation where you have something hot and high pressure that is expanding. Again, quick review on this, in case you want to know more. So as I said, this is quite a fast-driven wind. Observationally, it's not been so easy to actually see these expanding shells from stellar wind. So here is like an attempt to, so now we're in Orion. So this is observational work that we're measuring the expansion of some identified bubbles. And we see relatively modest expansion velocities here. So this to me it's not necessarily obvious what's really happening there. Similarly to before, we could look at the classic solution for these winds. Of course, this has already been done in the 70s, just as before. So this is the classic Weaver solution for stellar winds that gives us the radius as a function of time, of this bubble that we have. And we could again rearrange this in order to get the time scale. Just as an aside, of course, once we break, as I said, this idealized situation of a spherical cloud of uniform density, things become a little bit more complicated. In particular, this is some recent work that looked at what happens when we have these wind bubbles in more realistic turbulent environment. And what they have modeled is that you have this layer at the periphery of the extent of this bubble, where you have efficient turbulent mixing with the material around it, and then it cools much faster. And then this expansion becomes a lot less efficient. So just to compare here, for fixed cloud radius, we would reach it with the old solution at like 0.2 million years versus 1 million year with a new solution. So it really slows down everything. The same group has also modeled this numerically, and they do see this behavior. So it's not just an analytic prescription, but this has also been modeled more extensively. Okay, and then I will quickly go through radiation pressure as well. So, as I said, even if the radiation cannot ionize the medium, it can still impart momentum. And we could have this done directly when we have absorption or scattering of photons by the gas or dust, or it could happen indirectly where the dust will absorb this radiation, but it emits a photon in the infrared, and then that photon will then exert pressure. The thing with radiation pressure is that you need to have the interaction between the photon and your dust grain. If your gas is optically thick, then you will have efficient interaction, and then there will be some significant radiation pressure that's actually transmitted into the material. But if you have optically thin situations or low quantum densities, then nothing much happens there. There isn't anything to interact there. And this could be of course parameterized to describe how much of the momentum is actually absorbed by the material. So what we believe, because of this condition that you need high column densities, is that radiation pressure is really mostly important for small regions with high opacity, so fairly close in the relatively early stages of star formation when you still have a lot of material, and then becomes a lot less important later on. Similar to the previous ones, we could, this would be another argument related to the fact that we have optically thin situation in the gas with typical GMCs, densities like this has to go really way up in order for the optical depth to become significant in the infrared, at least. But similar to the previous situations, we can also obtain a time scale that would tell us, if we only had radiation pressure and nothing else, how long would it take for a cloud to be dispersed? I've already given you away the fact that it's not going to be very efficient. And finally, we have supernovae. As we are all aware, they input a huge amount of energy and momentum into the ISN. Or at least they have a huge energy output. How much is actually absorbed by the ISM depends on the exact conditions in which they explode. So so here we have very much of a environmental dependence, which is illustrated very nice in these simulation snapshots. So in the first snapshot here, supernovae were exploded from the density peaks that occurred in the simulation, versus supernovae that were just randomly scattered all over the simulation, versus ones that were clustered. And you see that the outcome is, even by eye, quite different. So if the supernova explodes in a very porous environment, then it will have limited capacity to actually push away gas, because a lot of its energy momentum will be lost. A few other things here about supernovae is that while the other mechanisms start to be important pretty much straight on, with supernovae we have a delay, because they happen at the end of the lifetime of the massive stars. So first of all, if we consider the shape of the IMF, most of the supernovae progenitors will be from the lower mass progenitors. So these will be the longest lived supernovae progenitors. And for the purposes of this, we assume that the low mass progenitor is 8 solar masses or more. There's some wiggle room about what's the lowest mass star that can explode a supernovae based on our understanding. But also we have some limit on the upper end, because at some point we believe that a star over a certain mass will not really explode as a supernova anymore, but it will instead just directly turn into a black hole. So we'll skip the entire explosion part. And reasonable estimate for this is 20-ish solar masses. There's lots of models for these things. This one is actually some observational constraint that looks at various observations of supernovae and finds that 20-ish solar mass is kind of reasonable based on what we've seen. But of course, this means that if we are limited to only 20 solar masses, we will in fact exclude all of these higher mass stars, which are much shorter lived. So this would be something that would give us more or less, not instantaneous, but this would give us feedback much sooner. Whereas if we're limited to 20 solar masses, we're looking at a lifetime of 10 million years. That is a bit long compared to what we will see as typical for the other feedback mechanisms. So now that we've reviewed all of the different feedback mechanisms, let's try to actually figure out how they impact GMCs and galactic scale environments. So I unfortunately have more questions. I don't think we necessarily have more chocolates, but
You have 3 more chocolates, spend them wisely.
okay, very good. Okay, so here is a list of things that feedback from massive stars can do to GMCs. It can heat and ionize the gas. This is not controversial at all. We see all these bubbles everywhere around us. We see the H2 regions. This we're fairly confident about. Here's another statement that feedback from massive stars can disrupt GMCs. This is a little bit harder to see because this is a dynamic process, right? So like we can't play it forward in the real universe. We have reasonable evidence, but yes. And by disrupting the GMCs, feedback can then limit the star formation efficiency. This is an important one, but the two of them are quite strongly related. So of course, if we form stars, but at some point feedback disperses the native environment once these stars are born, then not all of the gas from the original cloud will end up in stars. This is what limited star formation efficiency means. Star formation efficiency is just what part of the gas that we have available ends up in stars. And we know observationally that we have low star formation efficiency, so it's important that we understand why this happens. And also, yes, feedback can impact the IMF. So I'm going to look into these in a little bit more detail. But first I wanted to ask you, which one do you think are going to be the dominant feedback mechanisms on GMC scales? Of the ones that we were just discussing until now. This will give you a chocolate.
What physical scales are we talking about? 100
GMC.
parsec, 10 parsec?
I mean, it depends how big your GMC is. But okay, let's say between 10 and 100 somewhere.
Unknown.
Hmm?
Unknown.
Unknown, okay. Wise choice.
You need a star formation efficiency.
Yes, I think this would definitely happen, but yeah, but which ones of the ones that we discussed do you think would be most important? Do you have any thoughts on that? That's fine, that's fine.
Depends on the simulation.
Don't put that on us.
That's a totally.
No chocolate for people insulting city.
Thank you.
But it's a simulator, isn't it?
Oh no, I'm saying that's too much pressure to tell me that nature's actually caring about my simulations. I thought it was the other way around.
Okay, I will keep you in suspense. No chocolates.
Oh, hand up at the back here.
Yes.
Yes.
But not to answer. It's another question.
Yes.
Maybe I'm kidnapping a little bit the question, but from extragalactic scales, there is this trend now or open discussion about positive feedback. And you have outlined the whole feedback mechanisms. I don't want to say like this, but with the negative point of view for the gas surrounding and the gas helping in the star formation. What about the counterpart? Like there is some mechanism also enhancing the collapsing process, or that's not a possibility?
I would say depends on your simulation. I think it's a lot more complicated than that because we have. It's not like if you have one GMC and then you manage to disperse it, all this gas disappears and goes nowhere, right? So it does feed back into the galaxy. You said on galactic scale, so presumably you don't mean like...
No, I mean, I'm extrapolating the picture that people are discussing in extragalactic scales. Like, for instance, the action of many of these mechanisms at the same time can be inducing the opposite effect. Because, for instance, stellar winds, you said that they also help in changing the time scales and the cooling time scale for the gas. So maybe the action of simultaneously more of one mechanism, which is expected to happen, I would say, can somehow enhance instead of preventing or disrupting the EMC.
So I think there's evidence, I was wondering about this at the beginning of the talk, from the PAUSE survey, Sharon Knight's work. She tries to get GMC lifetimes in the Whirlpool galaxy, but they basically see a correlation where the clouds enter the spiral arm and they're triggered. Like maybe there's a compression because of the potential, but they don't, so there's like a difference between the lead and the lag properties of the material that you can see, and it looks like the star formation, these things go in, get compressed, quote, destroyed, but anyway, they convert some mass to star clusters or stars come out the other side. In this case, they're using that to estimate the GMC lifetime, but to me, it's an example also potentially a form of positive triggering, knowing that also the negative feedback is in there too, right? Because they're forming, anyway, so it's like kind of a mess. But anyway, I think that's really interesting as well.
I kind of view this as a time scale thing where you have swept up gas on the leading edge of some compression wave generated by your feedback processes, and stars may form in that shell faster than they might have otherwise, but that was part of the cloud. You've just sped up the process, and the cloud is on its way to being blown to pieces anyways. So on the lifetime, like if you talk about like sub-cloud lifetime scales, then I think positive feedback is happening all over the place all the time. But it's kind of like you're doomed. Once you start forming massive stars in a cloud, that cloud is going away one way or another. And so like little patches of it might be partying at the end of the world as they're being swept up by feedback shells. But if there was any kind of situation you could get in where the stellar feedback was net positive on all scales, both in space and time, then it would just be a runaway process, and you would convert all of the gas into stars, and there would be no evidence of like outflows or shells or things like that.
Thank you, Ben, for the absolutely excellent explanation. I hope that people on Zoom can hear it.
Oh, sorry.
But
For once, not talking loud has hurt me rather than helped me.
Yes, but I mean, this is very important to consider, right? Because in case anyone could not hear, we were talking about triggers, star formation, and situations in which feedback would be positive. And Ben made the point that on short scales within individual GMCs, there could be triggered star formation. In the sense that the feedback can enhance density contrast and help prolong star formation. But if you were to consider a net positive on a galactic scale of the feedback, then you'll have a runaway process in which star formation will be happening very rapidly. I hope this was a decent enough summary. Okay. Any further questions related to this? Or should I continue? I will continue. Okay, so let's go back to the timescales that we were talking about beforehand. So, yeah, we're not even considering the jets and outputs here. We're just going to consider the ones where we calculate timescales. As a reminder, we have a bunch of equations. Their specific form is not too important. But here I will show you what happens if we plug in typical values in the case of one specific galaxy. So here we're looking at clouds from AUC 300, which is a galaxy, even a simulator like knows that. So here you have the different feedback time scales associated different feedback processes as a function of galactocentric radius with typical properties for the clouds. And we see that radiation pressure is the one mechanism which really stands out and that requires a long time in order to disperse these clouds. Supernovae are placed like here-ish at like 3 megayears. Which, as we discussed, there is a bit of a band there depending on how well we feel we understand supernovae. But there is going to be at least 3 million years of delay. And then stellar winds and photonization are actually kind of comparable and are a bit over 1 million years for this particular galaxy and its clouds. And the data points that you're seeing here on this plot were then measurements of the feedback timescale for the clouds from this galaxy based on a statistical method, which I'm not going to talk about today. I believe that Mark is going to talk about this tomorrow. Yes, so at least within this type of measurement, it seems to agree with the shorter time scales that we would expect from photonization and stellar winds.
So, Maya,
yes.
I would like to question a bit the validity of those analytical equations, especially for the UV radiation. So my impression is that they are valid for a single star. So if you have a single core, when you turn on the ionizing radiation, there is no more accretion plus minus some residual. But on cluster scales, the amount of ionizing photons can continue increasing with time if you have more massive star formation, and the massive stars can be located at different parts of the cloud, so they do not necessarily can be treated as a point source in the center.
Yes.
The same thing with the stellar winds, etc.
Yes.
Radiation pressure is the opposite, so you have like an average cloud density, but at smaller scales, radiation pressure will act more effectively on smaller scales. If you have like an optically thick structure locally, so yeah, I have a lot of doubts with this analytical comparing timescale game.
Yes, I mean this was very much of a back of an envelope kind of calculation. I agree. Ben, do you want to say something, or because you look like?
Oh, yeah, I guess I am just resting, but okay. the other, like, you're right that these are all under an assumption of spherical symmetry and a constant, like, stars form instantaneously. You can actually modify these quite easily to have a continuous or varied star formation rate. You still end up getting power law solutions just with a different exponent. The thing you can't do to modify these and still have a closed form solution is have a full 3D turbulent environment. You're describing a simulation and not an analytic calculation. There's one other big caveat to these as well, beyond spherical symmetry, is that for most of them, like the Weaver one in particular, and I believe for the Spitzer solution as well, there's an assumption of zero background pressure there. So you cannot get a self-similar solution for a shell like this unless the interior pressure of that shell is vastly larger than the exterior, to the point where you can assume the external pressure is zero. So there's a whole handful of reasons why you need a simulation to do this right, but then you're in the situation where that's hard, and doing an analytic calculation is easy.
Thank you. All of that said, I was about to show you a simulation.
So much setup, great.
We've clearly practiced this before. Okay. but I mean, it's a very fair concern, right? And I agree that it's not at all as trivial as it is described here. Okay, let's see the simulation. So this is a simulation from the StarForm project, and there's no way that this is going to look anywhere nearly as nice on this as it will be on your screens when you look it up later on the internet, because it's on the internet and it's amazing. You should check it out. So this is a star-forming cloud, which is currently collapsing under its own gravity, and as you can see, there's a lot of substructure. There's some sheets and filaments that are being formed. There's going to be not much going on for a little bit until the first stars appear. But this is a simulation that has several different types of feedback that we're going to be able to see. So here we're starting to see some dense cores, and if you squint, you could sort of start to see some jets coming out. But they are still relatively low mass, so then the jets are not super powerful. More material is being accreted onto them. And very soon we should be able to see like more substantial jets. So there's like one over here. There's going to be one in the foreground, like over here very soon. There's like a few smaller ones in that corner. Yeah, here, this one. And yeah, so for a while, we're mostly going to be seeing jets, which are going to get stronger and stronger. Yes, finally. So we see these jets. They're not, I mean, they have some effect on their environment if you look at how the gas is moving, but they're not making a huge difference. But now we're having these bubbles from the high mass stars, which are, I guess, some combination of winds and ionizing feedback, which are expanding. The thing with this type of expansion is that initially you see these nice shells, but the moment they reach the low density environment, then it's really hard to see these shocks that they create anymore. So now it's just kind of a mess, but you have to trust that the ionizing radiation is somewhere in there and it's doing things, and ionizing material. And we will really properly notice this once we have this cavity, this blown out internally. We're almost there. So as the camera pans around, you will see that the internal region of this cluster that is now formed has actually been evacuated from most of its gas. Yeah, you see these now very low density regions that are happening. But it's a mess. This looks nothing like my back-on-envelope calculation, right? And towards the end of this, we will also see a supernova. This is a long video. But I'll try to point it out to you. Yes, now you could really see that all of this low density material has been pushed away from this cloud. And what we are left with were the parts that had a high column density, so they could not be pushed away quite as efficiently, and we have these like finger-like structures. That was a supernova, which is the color form. And that is now pretty much the end of the simulation. Do check it out. It looks
the change of color, it's this density, the color scale.
That's a very good question. I think it's
No, it's just when the supernova exploded, then it got all green. I was wondering, are we looking, so it's like density has changed, the temperature changed. We don't know if it's density.
Because the gas didn't look like it moved.
So
it's very puzzling. It looked
I
like
can
it had
answer
no-
that.
Okay.
So that in those movies, the color is temperature and the opacity is the density. So the opaque regions, regardless of color, is telling you the density. So that flash to yellow is basically as the supernova goes off and its ejecta goes all the way out to the edge of the cloud effectively instantaneously, it shock heats the dense stuff and its temperature goes up as well. So I think that yellow corresponds in there
It's
too.
not moving anything. There's the
No,
it just didn't
you-
go
you-
anywhere. It just all switched color.
I think that's one of the cool things you can see there is that porosity. The hot gas from the supernova ejecta is so diffuse that it doesn't even really show up in the opacity of the image. So you don't see the hot ejecta moving out. But what you do see is that it very rapidly heats the remaining material, and it's going to take a long time for that colder material, I guess, to actually get entrained and pushed out. So it's that idea of like a leaky cloud or a champagne flow. The hot material takes the path of least resistance, and the cold material basically only sees it once it's had enough dynamical times to catch up.
Thank you, Ben. Yes. So I don't have that much time left. We had some really good discussions. But let me just say a few words about the jets. So they were not completely useless. They might not be able to disrupt the GMCs. But what we see at least in simulations is that when we don't include protostellar jets, we don't get the correct IMF. So they are quite important for actually producing the IMF that we would expect to see in the real universe. That's all I'm going to say about this one. So I can mention a few things on galactic scales in my last remaining few minutes. I could ask more questions here, but I think in the interest of time and the interest of chocolates for the afternoon, we keep it to this. Okay, so we've already seen that feedback limits the star formation efficiency on cloud scale, and by extension, I think it's reasonable to assume that we could generalize this to regulating the star formation rate on a galactic scale. I think everybody would agree that that would be the case. What we also see in simulations where we could really switch on and off the different feedback mechanisms is that feedback can actually change the morphology of galaxies. And it's then also less controversially maybe related to how much galactic outflow we get. But I will try to illustrate what I mean by changing the morphology of galaxies. So here you get 3 different simulations with the same initial setup of different feedback mechanisms. So the supernova only feedback in this galaxy is creating these huge holes. Photoionization only is definitely not doing as much. And then supernova plus photoionization does something in between. So we do see morphologically different galaxies if we include different types of feedback. And similarly, earlier we talked about different supernova delay time based on the supernova masses. If we have more delay time between the formation of the supernovae and when they actually explode, this gives them the opportunity to move around and also for their environments to be maybe changed from other types of feedback, so they explode in lower density environment. But just by considering different delay time for supernovae, we could get very different looking galaxies. And this is Ben's work, and if you're interested in this, you should talk to him after this at lunch. So, yes, we should hear about these small scale feedback mechanisms also on galactic scales. And this is another illustration of this, where we would have a supernova only simulation versus a simulation that has empirically motivated subgrid model. Again, I'm not going to go into detail. This is Ben's work. If you would like to know more about this, please ask Ben. Here you see in the gas, we do see by eye different structure, but also when we look at the stars that are produced in these galaxies, we see very different kind of distributions. So this is way clumpier, and this is way smoother. But then, interestingly enough, if we compare something like the star formation rate, it's more or less the same, even though the morphology is quite different. So if we just looked at the star formation rate, we could think that, these guys were the same. However, in the supernova only case, we have a bit more outflow than when we included, the early feedback. So counterintuitively, when we have more feedback, we could actually get less outflow. So all of these things, even though they're happening on such small scales, can have quite profound implications on the galactic scales. And with this, I think I am pretty much out of time, and we are at lunchtime. But yes, I'm going to leave you with a few questions that you might want to ponder about and have more discussions maybe at lunch. Thank you.
All right. Time. If anyone has any last burning question. All right. One question.
Yeah, I want to mention this because it wasn't quite correct, something that you said, and it's not your overhead. So if you go back to the slide where you had the masses of the progenitor supernovae. Yeah, that one.
Okay.
Those are masses for red supergiants that explode. So those are masses for progenitors of type 2 supernovae. No one knows what is exploding in 1b and 1.6 nowadays. People thought they were Wolf-Rayet stars. Maybe they are. So no one knows, but they're probably coming from further up. So it's not like that you have to stop there at 20.
Okay, thank you.
And also there are now more than 100 superluminous supernovae, which are especially associated with the low metallicities, which are associated again with the massive stars, much more massive than 15 and maybe. Sorry. Now I wanted to point out with the surveys that are coming in, ICPTF, I don't remember the names, but they find also superluminous supernovae associated with the metal poor environment, so dwarfs, and those masses are much higher than 15, 20. So it could be an observational bias, either the selection of the type of supernovas was suggested, but also because supernovae are happening in dusty environment, H2 region, so there are geometrical effects as well.
Yeah, thank you. That was very good comment.
And at that point, go to lunch.
Thanks again from Maya for jumping in here. She feels a very important topic. Back at 4.